medical microdevices. Today's first speaker, Dr. Shripad Raja, is from Intelligent Software. I request Kaushik sir to just felicitate on behalf of organizing committee and NIT Silchar.
Yeah, so Dr. Shripad Raja, thank you for accepting my invitation and agreed to deliver one talk on specifically on the hands-on training and learning session. So because we could not host you in the physically due to the situation, so we are conducting the workshop virtual. So obviously at the same time, we also would not miss the chance to felicitate our speakers. So please accept our virtual felicitation with a very traditional Assamese gamucha and the flower bouquet. Please accept our virtual felicitation and thank you.
Thank you very much. Very nice of you, and it's nice to work with you as well.
Yeah, over to Ganraj.
Yes. So I'll be giving a brief introduction to sir. Dr. Shripad Raja sir completed his master's in electronics from Bangalore University in 2007, and further with a PhD from NIT Surathkal. He started his career in MEMS as a project assistant in IISc. Later, he joined Big Tech in 2009 as an application engineer. He was a senior application engineer after the Intelligent Software team set up a new company, Sridath Technologies Private Limited. He has conducted many training programs and has given many invited talks all over the country. He is associated with the Intelsense and its associated business for the last more than 12 years, and is representing India. He is now operating as in the capacity as a manager, applications and sales Intelsense Software USA. So till now, in the last 4 days, what we have seen is we have seen a lot of BioMEMS structures. So and its application in the field of medicine. So today we shall have some hands-on training so that we can have an how to design a particular MEMS structure. So we'll be having an overview of that. So today, Dr. Shripad Raja sir will be guiding us in designing some MEMS structures. And today's talk, it would be more on surface acoustic wave devices for fluid applications. I welcome Dr. Shripad Raja sir. So to go with the session. So please share your screen, sir. So
yes, thank you.
Yes.
Thanks, Ganraj. Thanks for the introduction. So I'm sharing my screen. So hope you are able to see my screen now.
Yes, sir.
Oh, nice. Okay. Yeah. So my session is until what? 11:30, is it?
Yes, sir.
Yes, yeah.
Right. Okay. Correct. Okay.
So maybe I think you can continue up to 11, 15, 20. So 5-10 minutes interaction. Then 11:30 is another speaker.
Okay, fine. Okay, thank you. Thanks for the introduction and also the virtual felicitation. It's nice to get connected through NIT Silchar again because our association goes quite some years before. Thanks, Dr. Kaushik Guha, and also the NIT Silchar-ATAL workshop committee for giving me a chance to share some of my thoughts on MEMS devices. Here we'll be talking on how to do a surface acoustic wave, how to design a surface acoustic wave device using IntelliSuite software. So the title of the session is a hands-on session, but we are physically not giving you a hands-on on the software at all. So since this is a virtual event, virtually having a hands-on session is extremely difficult to monitor many participants. So what we have done as an arrangement is that we run through the session here, and then those who are keen to explore the software with a hands-on session, a video tutorial of how to simulate a device can be shared with you with a 15-day trial license. So in that way, you will also get the experience of how to use the IntelliSuite software. So the intention of giving you a hands-on session, the purpose will also be served. Okay, yeah. So here, let me run you through a 10 to 15 minute on what IntelliSuite software is all about. Okay. So here, since you have gone through all the introductory part of what is sensor, what is MEMS sensor, so let me not talk about anything of those things. Last 4 days, many experts from various academic and defense labs have shared their experiences and also educated you more than me. Okay, so let me directly jump on to the software. Okay, so here when the devices are being used, so MEMS as a combination of sensors or an actuator or a sensing and actuation, the combinations are both. So here we have thermal forces or electrostatic forces, magnetic force, hydraulic force are some of the driving force for all of these MEMS devices. And we have some sensors on piezoelectric crystals and few materials like shape memory alloys. Okay, so we have that. So now when we look into the design specification of any device, so we need to consider three parameters. One is mechanical, one is thermal, and another is electrical. Based on the sensing part of it, it gets decided whether it is mechanical thermal or thermal electrical or electrical mechanical. So what combination it is. Okay, yeah. So I'd like to mention that in case if you have any questions in between, then and there you can stop me and get it clarified. Okay, you don't have to wait till the last minute. Okay, so you can also ask me questions at the last round during the question and answer session. But in case if you want to raise a query in between, you can do. You feel free to do that. Okay, yeah. So as such as a design requirement, so we have the design requirement that we collect, we do the basic design and optimization. In the software, we go through the CAD model and we do thermoelectromechanical, reduced ordered model simulation, and SME, system model extraction, and SLI, system level integration. Once the device is simulated and well working in the requirement area, then we move to the layout. We create the layout, process optimization, fabrication, and testing. So this is the overall overall procedure that any MEMS design engineer uses. Okay, or the MEMS team uses it. Okay, so here specific to the software IntelliSuite, how do we cater them? So generally in India, most of us focus on multiphysics software. Okay, so here multiphysics software is more like designing a CAD model and then simulating it. Okay, and so a 3D CAD model can be created and optimization can be done using the FEM software. Okay, another parameter that we all need to look at is the system level simulation. Okay, so the integration of CMOS with the FEM with the MEMS device is equally important. Okay, I would like to take an example. We have 5 sense organs. Okay, if the brain does not work, then what is the use of the 5 sense organs? Okay, so similarly, a sensor is an excellent thing, but it gets a value when the signal gets processed and it is come into the readable format. Okay, so that's very challenging, and probably most of us have to explore in this area. Okay, another parameter that we generally don't consider is that the process simulation, because most of them who try to fabricate the device usually have this issue that the simulated output does not match the experimental data. Okay, so that's a usual problem that we all face. Okay, through many programs, we try to fabricate the device, but this is some of the issue that we will keep facing. Okay, so for that, what we do is a process optimization technique is implemented. So in case if you are a process engineer, you can use the software to finalize your process and also predict what really happens when you really fabricate the device, because what we have as a software, the clean room simulation, is purely based on experimental data and the physics of the fabrication. Okay, it's not the emulation of which the other software provides. Okay, so you can use that. So that is one way of doing it. As a design engineer, what you can do is you can use the process model to export it to FEM and then simulate that data. Okay, so first do a CAD model, try to finalize, do a process driven model, and then see the working of it. You will see a completely different output altogether, because the process models are completely different from our CAD models. In directly when we do the design in 3D CAD models, and that we take many of these dimensions as ideal conditions, but those who have really fabricated the device can understand that it is not the same dimensions that we can get, okay, when we try to fabricate it. So it's important that we consider the process driven models. Okay, so when we are looking at the challenges that we face in 3D CAD model, so we have the 3D CAD, FEM simulation, parameters we define. So how do we offer a solution is a parametric structural, parameterize the structural, tell the software these are the set of dimensions I need to work on, and then you do the simulation for me. So you define the range of values of dimensions, and then software can rebuild the structure multiple times, and then it can simulate it. Okay, parameterize input variables, system model extraction, and reduced ordered model. We also have something called as element-based modeling, system level simulation, where we can parameterize even the structural at element-based models and also the input variables. Challenges in the modeling of process-driven models is that it is a layout-driven. Once the layout is created, a process recipe is driven, and then and the process integration happens. So we do the lithography process, okay, and then we do the etching. So usually we most of the times we face this issue of undercut and overcut problems. Okay, so for that, so you can plan to optimize the mask layout accordingly. That is one advantage. And another is the design rule check option. Design rule check is something which is specific to a foundry. Okay, assume that you are trying to fabricate some device in an academic foundry somewhere. There are many foundries in India, so some foundry. So they have their own design rules. Okay, so based on the design rules, you can design it. Okay, and so here you can create a template of the design rules and then give it to, or you can run that. You can collect the design rules from any foundry and then create a template and run the template on your mask layout, so that it will tell you whether the design rules of that specific foundry where you want to fabricate, whether your design fits into their requirement. You don't have to approach anyone else to get it corrected. Okay, you can do the process verification also. Okay, so here when we specifically talk of multiphysics, we have coupled FEM and BEM solver, and some of these examples, non-linear and linear models are also available. And our specialty lies in also on the reduced ordered model simulation through the system model extraction. You can see that this FEM model, what you see, can be converted to a reduced ordered model, and in the black box, what you see is the FEM model, which is connected to a circuit. Okay, so everything can be done within the software itself. And another is the thermal packaging analysis. Of this example is specific to gyroscope. So thermal packaging analysis is also possible. So what all benefit that you get is you can do a 2D and 3D CAD model, and a preprocessor is there to set the settings for larger structures. Larger structures meaning array-based structures, something like a microphone, sometimes pressure sensor, sometimes micro mirror. So work in an array. Okay, when in an array, the structure becomes too big. Okay, for that we have a preprocessor where you can set the parameters, and it saves a lot of time because you can parameterize the structural dimensions of the device. And also the post processor is for visualize with more graphic based results, and then a macro model simulation which can help you to verify your FEM results with a Lagrangian based output. Okay, we have element based modeling, so where you can drag and drop the elements of beams and metal element, plate elements and comb structures, and then you can even connect them to the circuit. Okay, so the design which you create in element based modeling can also be pushed to FEM model and also to the layout file. So what we have as a benefit is a schematic driven design, and which saves a lot of time, and the results can be viewed on 3D. The microfabrication, when we look at it, it has 4 major steps: deposition, lithography, etching, and bonding. Okay, so we have these 4 steps with different materials and different processes for different materials. Okay, so that's what we will see. So here the advantage that we have is that in case if you are looking at research opportunities in MEMS simulation, so here in India, most of the MEMS simulations or MEMS activity happens in the academic space. Okay, whereas outside it, though it happens in academic, most of the government labs and also many companies work on MEMS devices. Okay, so since March 2021, I've been exposed to the global application engineer kind of a position. So I interact with most of the people in the West. Okay, so I've realized that MEMS is scaled up to the industry level. Okay, so here specific to research opportunities, when we look at here we can parameterize structural, we can parameterize input variables. And how do we do that? So let's take an example of MEMS accelerometer, where we can see that the natural frequency changes with different length in the beam. So you can tell the software that these are the set of dimensions. So I want to vary the beam length from 100 micrometer to 200 micrometer in the increment of 10. How does the natural frequency change? So you can tell the software by feeding the appropriate values, and then you can get the parametric output. Okay, so something like a comb structure, a piezoelectric beam kind of a structure as well. So we can extract all of these models, and then we do the system model extraction, where we can do the signal conditioning system prepared connected to a FEM model. So what you see is the center box is a black box of a FEM model, where the output of the FEM model can be connected to a signal conditioning system with a feedback loop, no feedback loop. So those are the circuitry part of it. Okay, so what we get as an output is that the reliability, reliable results, as we are trying to benchmark with Lagrangian and FEM models, and then a comprehensive study with the structural behavior, the behavioral study with range of loads. So when we do a parametric simulation, both in terms of input variables and also in terms of the structural model, we get more clarity on the device working. So it becomes easy for us to target any application. Okay, so the advantage of using element-based models is that the elements can be used to create any kind of a device. So here you can see that these elements can be used to create a cantilever beam, a resonator, or a gyroscope, or an accelerometer. So various devices can be used, can be created using these element-based models. So here we can also parameterize the structural and also the ambient conditions. Okay, what you see is the thickness. If an accelerometer, if I vary the thickness and parameterize the structural, how does the amplitude of vibration reduces with change in thickness of the structure? You can see this. And similarly, in case if the ambient condition changes, like I'm changing, in this case, I'm changing the pressure. The pressure around the device changes. What really happens? So these are extremely important because the ambient condition are the factors which creates damping, which causes the damping in the device. Okay, so these are critical important. So in FEM software, in FEM simulation, we specifically define zeta value, that is the damping factor. Okay, a range of damping factor we can define and we can check the performance of the device. But what is the zeta value really the specific value? May not be, or it can be. Okay, it's doubtful, it's debatable. So here you can define the pressure ambient condition, something like the mean free path and the viscosity of the gas that is around, and or the fluid which is around, and also the pressure around it, and the temperature around it can be defined, and we can get the output of the device. So what is the outcome when we do a FEM based model is that results are ideal unless otherwise. I use this word unless otherwise because unless we define a zeta value, whatever the output that we get is all ideal conditions. But whereas in this, in the case of element-based model or the reduced order model simulation, or simply call it as a system model extraction, or sorry, system level simulation, we have the results based on ambient conditions. Okay. So here, when we want to do fabrication, so there are few templates which are available, like the MEMS process. MUMPS stands for multi-user MEMS process, which is a template. It is more like learning a programming language with a standard exercises. Okay, when we really learn any program, we try to create run few programs where if we are learning C++, we first execute hello world. Okay, something like that. So standard programs we create. When we create a digital circuit, when we want to learn about digital circuits, we start using adder, subtractor, so kind of a circuit. So those are the standard ones to understand. So here MEMS are the ones which will help us to understand the process, and we can build devices using these MEMS process, and these templates are integrated in the software. Okay, once we gain some confidence in any subject, we try to create our own way of methods to understand. So similarly, we have a custom process driven flow. So usually MEMS process is custom driven, but again, there are two advantages using the MEMS process. One is, major benefit is you don't have to really worry about the process recipe. Another is the cost benefit. When you try to fabricate the device using MEMS process, the cost substantially comes down because there is no process engineer who has to define a specific process flow for you. Okay, MEMS process is anyway set as a standard, so the fabrication can be done. Okay, but when it comes to custom process, it becomes expensive. Okay, and we have extensive material database with a process traveler as well. Okay, so here this is an example of a custom process. A custom process where on the right side, what you see the video is a nano hole array, which is used as an optical waveguide. So what specific to the process, what you're seeing is a DRI process. Okay, so we are trying to create a nano hole array for any optical waveguide or optical resonator kind of a structure in the nano scale. Okay, so and this is the process that you can see. Okay, so we can define the custom process as well. So you can push it to PowerPoint. So what you see, the PowerPoint presentation, so this structure is created, this PPT is created by the software itself, capturing the images of the nano hole array structure with all the details. Okay. Okay. So you don't have to really create the structure using blocks. Okay. And another parameter that we come across is the fabrication, one of the major challenge is the etching process. So when we want to do etching, we do a KOH etching. When we want to do etching of any material, we either ask two questions. One is whether it is crystalline in structure or metal or oxide. So we simply call it as surface micromachining or bulk micromachining. So when we talk of bulk micromachining, we again two questions, whether it is dry etching or wet etching. Again, when we talk of wet etching, again we have question, what is the etchant? KOH, TMAH, TMAH plus Triton, or KOH plus IPA, what combination? Okay, so when we again further go down to that, what is the time of etching? Okay, what is the etch rate? So there are many questions that keeps coming down as we go down. Okay, so what you see here is different profiles are created using KOH etching on different orientations. Okay, so here you can see 100, 110, 111. Same mask is being used. The orientation changes. So here TMAH is used. So why TMAH is used? TMAH is widely used for IC design when we try to fabricate any IC, because KOH, this K plus ion leaves some charge residuals. Okay, so it is not good for IC device. Okay, when we are trying to fabricate using any IC. So for that we use TMAH. So here same TMAH etchant on different orientation generates different profile. Okay, so we have quartz. So let me skip this, and also sapphire. So basically three types of bulk micromachining process. One is the isotropic etching, anisotropic etching, and plasma etching. So the same mask layout is being used for different profiles are created based on the choice of the user. So when we talk of KOH etching, you can see the profile that is generated. A square mask is taken. Those who have no idea of fabrication, there are some for them. You can for them it's a message that when we try to really create the structure or on the silicon, a square profile needs to be generated. We think that square mask is used, but not. So here a square mask with KOH etching, when it is used, the profile is created like this. With KOH plus ICA, we have a smoother profile and also at least fairly we can say it's a square from the top view. When we use TMAH as a raw, this is the a raw chemical. So as we get this profile. When we add Triton to it, which is a surfactant, then we get a smoother profile. Okay, so the process engineer needs to explore all of these possibility before trying to fabricate. So hence the cost of fabrication goes high when we talk of custom process. Okay, so here those who are process engineers face a lot of challenge on creating the mask files. Okay, what should be the mask? Because creating mask file is not that easy because there are a few issues like overcut and undercut problems. So here you can see how do we optimize a mask. So we can create different masks and you can see the structure. Here we are using a plus shape mask to create a octagon structure. Okay, so here on silicon 100, we have this octagon structure created using a plus shape mask. Okay, and when we look into 111 way orientation, we use two triangles meeting at an edge. So such kind of a mask is being used. Okay, to create a octagon structure. So it's not that we create octagon structure with the octagon shape mask only. Okay, so here such mask optimization techniques can be used. You can see the octagon structure is created. When we further etch, it becomes a hexagon. So etch time is also equally important here. Okay, so you can decide what should be etch time. Okay, all of these things are based on experimental data, so we can confidently talk about it. That whatever happens here is what happens in the clean room. Okay, so here this is a material with INP, indium phosphide material. Okay, where you can see that the orientation changes because of the orientation in the INP. Okay, INP is used most in the photonics space. So we have quartz. So here, in case if you are etching quartz, we have different orientation, Z-cut and AT-cut. Okay, let me jump in to the last part. So you can see the same mask, different shape of profiles are created. Okay. So this is to give you an overview of what IntelliSuite is all about. In case if you have any questions, you can ask me now. Further, I have another specific one to what the intended device for today's session is, surface acoustic wave device. Okay, if you have any questions now, we can discuss, or else we can jump in to the surface acoustic wave device. Okay, yeah, I'll wait for 2 minutes. So in case if you have any questions, you can ask me.
Dear participants, if you have any questions, so quickly we can take 1 or 2 questions before starting his next session. Actually, the next part of his talk. So if you want to clarify something on this part, so you can unmute and interact with the speaker directly.
Yeah, since I'm sharing the full screen, I'll not be able to see any of your messages if you are raising a query on the message and the chat box.
Yes, yes, yes.
Yeah.
So you can post your query in the chat box so that I can read also.
Yes, that's also possible. Yes.
Sir, good morning, sir.
Yes. Yeah.
Sir, it's Venkatesh from Save the Institute of Technology.
Yes, Dr. Venkatesh.
Sir, I wanted to know whether it is possible to fabricate large area dimension structures using IntelliSuite.
Large area dimension, what is the kind of dimensions?
Dimensions, see, actually, I have tried nanostructures, so that is working
Okay.
good. Suppose if the dimensions are large, can we go for example, large mode area fibers? So can I simulate large mode area fibers fabrication steps in the IntelliSuite?
Large mode. I mean,
Large mode area means
can
the
you talk of
dimensions will be
any
large.
millimeter kind of that kind of a dimension? Is it
Yes,
millimeters?
it will be in millimeters.
Okay, see, few millimeters is still possible. We have an option to create large structures, like at wafer level we can create it. Okay, so that is truly possible. But you are talking in terms of fabrication there?
In terms of application.
Oh, okay. Okay. Yeah, I think we can discuss, Dr. Venkatesh. Shouldn't be a problem. I think I'll get in touch with you specifically on that dimensional part. Let's explore it together.
Sure, sure. Thank you, sir.
Okay. Neeraj Kumar, on the KOH part of it, what we have is a dedicated module. So let me share my screen to one of the module that we have. Yeah, so here we have this IntelliEtch module specifically designed for wet etching of silicon, quartz, and sapphire. Okay, so here when we take off a new file, you can see that silicon substrate, you can choose the orientation. Okay, which orientation you require it, and also its XY dimension. Okay, so say 1000 micrometer to 1000 micrometer. I click accept. As of now, I've taken 100. Okay, so here you can define the mask layout. Let me take some random mask, something like this. I can flip this as a negative or a positive mask. I can put this as a nitride or oxide on top of this, and then we can directly go to wet etching simulation. Obtain from data. So you want to use KOH etching at different concentration and temperature. Okay, so you can do that. In case if you are using TMAH at different concentration and temperature, you can use it. In case if you are using TMAH along with Triton, so these are some of the standard practices that are used. But any combination that you wish to explore, typically we help the user to implement a file through our developers and then give a specific etch rate database for them. Okay, so you can use this. So for this, let me use this, which is a standard one, which is being used. I can define the etching. So here I can just run the simulation, and then I think it's done. It's a 10-minute small simulation. You can see that I can generate the profile, something like I'll remove the mask. You can see a 10-minute kind of a simulation. So it has generated this kind of a profile. When I further do that, so we can see the V shape, the angle plane also. Okay, so that way you can use this for quads also. For quads substrate also you can define it. Yeah. So did that answer your question, or you have any specific question?
Thank you, sir.
Okay, thank you. Okay, so any more questions, or should we start off with the surface acoustic wave device? Yeah, I think we can start off. In case if you have any questions, we can take it up later. Okay, so surface acoustic wave device as such. So we'll see some introduction basics of what is a SAW device and why we are trying to create a why SAW device is a very interesting device for two different domains of application. One is the RF application, and another is the BioMEMS or a chemical BioMEMS application. And we have types of SAW devices, and we have relay waves and love waves. What all the things that are there, we will see one by one. Okay, so typically a SAW device is based on the mechanism of piezoelectric effect. Okay, so here we know that in piezoelectric effect, when we apply stress or there is a movement, then charges are displaced, and then there is a voltage generation. The potential is generated onto that. So the second image what you see is the full SAW device. Okay, it has three parts. One is the substrate, second is the IDT, what you see is the fingers is called the IDT, interdigitated transducer. Some people call it as interdigitated electrode also. Okay, on two sides we have it, and the center part is called the delay line. Okay, so there are two types of device, two variants in SAW device. One is love wave device, or called as a shear horizontal surface acoustic wave device, and another is a relay wave, which is a purely a SAW device. Okay, so what is the difference between the two devices here? Difference is that we have on the relay waves, you can see that the surface waves pass just like the waves are passing just like the ripples in the water. Okay, so the displacement is on Z and Y direction. Okay, on one side, sorry, Z and X direction. So the waves are standing. Okay, so this is the Rayleigh waves. And when it comes to love waves, it becomes horizontal. Okay, so the displacement is in x and y direction. So what you see is the shear horizontal surface acoustic wave device is a shear horizontal. The surface waves are in x and y direction. So the intention of generating such waves are for a specific reason. Let's go into the specific part of it. Okay, so basically a SAW device was first invented for RF application, and it is commercially available. So when you go back to any SAW device, you can see some of the scientific reports in 1970s also. Okay, so it was basically designed for a RF application, but later it was discovered the same device can be used as a biosensor or a chemical sensor or a gas sensor as well, which is simple to design and also manufacture, uh, which has varieties of application, and then specific device for liquid and gas sensing application. So here the liquid and gas sensing application makes the difference between a shear horizontal surface acoustic wave and a normal surface acoustic wave. So let's understand this. When it comes to rayleigh waves, you can see the same animation here, that the surface waves are on vibrating in the x and z plane. Okay, whereas in the love waves, you can see it is in the x and y direction. So usually when we are trying to build any gas sensing, where the sensing material, sensing chemical is a gas, then we use rayleigh wave type of a device. When the sensing material is liquid, we use love wave type of a device, because when we use a liquid on the delay line, so what generally happens here is that the surface acoustic, the input is given here. Okay, so let me probably show you in this one. I think I'll use this device. So one side of IDT is called the input IDT, and another side is called as the output IDT. Okay, the RF signal A sin omega t, you can say that, is fed to the input, and this IDT displaces on the piezoelectric device. Okay, when there is a movement in piezoelectric device, there is a potential that generates. Okay, and also when potential is applied, due to that the displacement, so the surface waves pass through it. And as a RF design engineers, we know that when a wave passes from one point to another point, there is always a delay, due to which there is a phase shift that happens. Okay, so that is taken as an advantage here. So we use this as a two device where, in case if there is a chemical that is being sensed, we use one device for that, and without chemical is another device. So we have a reference data where when a chemical is not being used, how the device performs, and when the chemical is being used on it for sensing application, how the device works. Okay, so we have a comparative data, and based on that we get the output. So how these things will help? So here we can see that there are lots and lots of application which are available. Okay, so for for chemical sensing or gas sensing, in terms of bio, on the healthcare also, we have a lot of applications. Okay, where we can detect sugar level, we can detect some of the enzymes. So there are a lot of applications that are there in the healthcare as well. Okay, so here there are few parameters to be considered. So these are the 8 parameters which is typically considered for a SAW device optimization. One is the SAW operating frequency, and the electromechanical coupling factor or coupling coefficient, reflection coefficient, gain. So reflection coefficient gain is purely your S parameter, this is S11 and S21. and the relative shift in frequency or velocity, mass sensitivity, limit of detection, and temperature coefficient of frequency. Okay, so here saw operating frequency. How do we know at what frequency that we can detect? So the first expression what you see is the saw operating frequency, F is equal to V by lambda. What is V? Is the surface acoustic wave velocity, and lambda is the pitch. Okay, pitch is the distance between the two IDT. So we call that as lambda is four times the width of the IDT width. Okay, so FV lambda. So here the velocity of the surface acoustic wave depends on the piezoelectric material that we are using. So surface acoustic wave in PZT is different, ZNO it's different, ALN it's different, and if any other piezoelectric material, it's completely different. Okay, so based on that, the frequency gets decided, and also the IDT width that we design decides the operating frequency. Okay, so typically it is operated in RF range. Okay, so we can consider somewhere around 1 megahertz to 500 megahertz. Typically all these devices fall in this range. Okay, if you look at the literature. Another thing that comes is the coupling coefficient. So we can calculate based on the velocity without the sample and with sample. Based on that we can see the coupling coefficient. The reflection coefficient is your S parameter, insertion loss, frequency shift between the input when the with sample and without sample, the mass sensitivity. Okay, so and limit of detection. Limit of detection is basically what should be the minimum quantity of sample that is required to see an output. Okay, limit of detection, and temperature coefficient. Okay, so these are the set of parameters which are typically calculated when we design and try to simulate the device. So if we can get very good values of all of these values, then we have a very excellent device. Okay, so this is a schematic of FEM simulation on thermoelectromechanical module. Okay, what you see is the IDT. On the left side, if I consider the first image, the pads, what you see, the square boxes, are the input feed, that is the input IDT. Okay, so we give A sin omega t, that is the RF signal, and in between is the delay line. We have a output IDT. Okay, so here when we give a input signal, that is A sin omega t, and that omega depends on what piezoelectric material that you are using and what is the pitch size of your device. Okay, based on that, your input A sin omega t, that omega gets decided. Okay, and we see this when we run the simulation. You can see that the potential distribution happens like this. Okay, so here when we are talking of gas sensing application, there are materials, there are devices which are being fabricated on silicon wafer itself. Okay, on silicon or SiO2. Okay, so it's being used, or quartz also. The sensing material can be coated on the delay line. So based on the sensitivity, and the sensing material can be decided based on what you are trying to sense. Okay, and the relay waves are generally passed on to it, and the relay waves see a frequency shift at the output IDT. That is the difference that we see. But when we talk of sheer horizontal surface acoustic wave, what really happens, why that is essential, because the device, if we use the relay waves, when we use the liquid sample, the liquid causes a damping on the surface acoustics wave. Okay, so the waves gets damped in the liquid region itself. It does not reach the output IDT. Okay, so hence when the waves is passed in the shear horizontal mode, that is in the XY direction, then the waves reaches the output IDT also. Okay, hence there is a difference between a gas sensing surface acoustic wave device and liquid sensing surface acoustic wave device. Okay, and how do we do that? There are few standard substrates which are designed for it. Okay, so something like lithium niobate and lithium tantalate are the two materials which are being used, piezoelectric materials which are being used at different orientations again. Okay, so based on the OEM, different orientations can be got through, and piezoelectric property changes with respect to the orientation also. Okay, so we need to be very careful when we are feeding all of these data into the simulation. Okay, so when we design and simulate that, we can see that there is a change in potential, something like a frequency shift that happens at one. So I'm giving a range some 5 megahertz to 20 megahertz. So I can see at a resonating frequency, you can see there is a phase shift that happens. And in terms of potential, there is a peak raise, okay, in terms of potential for a particular point, at a particular point. Okay, so this is how you can design. So let me show you the thermoelectromechanical module. So how do we design that? So I've set all the simulations. So first we do a dynamic analysis with piezoelectric definition, and then we okay, so I can show you here, like first we decide on the frequency. Okay, what is the operating frequency? 5 megahertz to 20 megahertz, 50 number of data points, we get it, and then we can get the output. What we have is this one. So this frequency versus potential, and frequency versus frequency versus potential data can be generated with dynamic analysis, where X independent parameter is frequency. Okay, once we define that, we define the material properties. Okay, in material property, we are very keen in defining the piezoelectric properties. So here, the advantage of using this material property in this tool is that you can even define the orientation. Let me show you that. So if you are specifically working on gas sensing application, and if you are using the substrate as quartz, so you can see that while you can define this piezoelectric property, so you can also define the orientation. So if you are using a quartz, you can see that whether it based on the orientation of quartz, you can define that. Okay, or else, yeah, if it is silicon, you can define based on silicon 100111. So, okay, let me not be keen on this one. So piezoelectric property is what we define. So in this case, the piezoelectric material is this one. So here we have this piezoelectric material we have defined. So this is the value of PZT by default values. Okay, and then we define static load. So we define this to be at 0 volts. This one 1 exponential 7. So really such big values when we define it is just to tell the software that this is a piezoelectric simulation, that's all. So this value, when we in IntelliSuite, if you have any value which is 7-digit, it is not considered in the simulation, but it is understood that we are trying to simulate a piezoelectric type of a simulation. Okay, so here we define the ground, that is 0 potential. This is the potential that we define, and then we can give a time dependent load. So here when we define the frequency, we can define the frequency potential on the frequency scale, but when we are trying to define on the time scale, so omega, that is the in terms of radians per second, we can define it. So based on the expression, here the expression, the value is given specific to B1 sine omega t. Okay, so the potential that is generated is 0.5 is given, 0.5 volts. Omega is 628 exponential 6 radians per second is the value that is given. And we fix the boundaries and then we do the analysis. Specifically on piezoelectric, for surface acoustic wave, the mesh should be very fine, extremely fine. So for that, we have this option. You can mesh only that specific region where you want it. Okay, substrate need not play a major role here. Okay, but now this is the case of a gas sensing. But when it comes to liquid sensing, the substrate itself becomes a piezoelectric material. So then we have to define the anisotropicity of the device. Okay, so the C11, C12, C13, these matrix. Okay, so what in literature for different orientations, we have to extract the elastic stiffness. Okay, based on the orientation of our substrate material, we derive the elastic stiffness. In case if it is not available and it's only a default 0 degree orientation values are available, then there is a method called as bond method where you can use it and then you can extract the elastic stiffness material matrix onto the device. So here for specific to these values, we define three major parameters. One is the elastic parameter and another is the dielectric anisotropic matrix and another is the piezoelectric stress or strain. So typically we get the value of strain, so we define this. So all three have to be extracted using the bond method. So it's a very standard and a simple process. It cannot be manually created. A simple MATLAB program can help us to extract the value of the using the bond method at different orientations. We can extract it. Once these things are defined, and then we run the simulation, a dynamic analysis. Okay, so dynamic analysis typically consumes a lot of time because here it has to simulate. I'm coming back to time scale again. So here we are trying to define something like 0.4 microsecond with 100 number of data points. Okay, so here, and the structure is also this big, so naturally it will take some a huge time, like something like this simulation on the we have a standard of 10 hours of simulation that it takes. Okay, so for such dynamic application, what we recommend is I think there was a message. Can you mention? I could not read it. You have any question? Okay, if someone can read the question for me, it's fine, or else I can see it later.
Sir, I have a question actually. I'm a
Yes.
participant. For the time-dependent analysis, whatever you have said for the software,
Yeah.
we have seen that for console it takes a lot of time when we do for time-dependent analysis. So here,
Yes.
like whether the time consumption is lesser than console or it is required more, because you said that the finer mesh aspect is always required here, but at times
Yes,
in
that
console
is
we
right.
see that for a crude type of a mesh also we can generate. So that is one question.
Yeah, so that's a good question, but specific it cannot be generalized with any specific. It's a generic problem. It's a FEM simulation. Even console uses FEM simulation. We also use the FEM simulation. Okay, FEM simulation are time-consuming simulation only. Okay, and in top of that, we have a finer mesh. Okay, so naturally, as I mentioned, this device itself takes about 10 hours of simulation, and I have an experience with working with lithium niobate and all. It has taken sometimes more than 2 days also. Okay, so it's a part of the FEM simulation, we have to accept it. That is one. Another advantage that you can to fasten the simulation is that we have this parallel processing setup. So in case if you have multi-core processor, then you can define it. So if I have an experience where on my laptop, if it takes 10 hours, on a PC when I tried to do it on a very good PC with 14 cores of processor, it has taken only about 4 to 5 hours of simulation for me. Okay, so you have that provision of using a multi-core simulation on IntelliShoot. That is one. And another advantage is that you can do a macro model simulation for a piezoelectric based models. Okay, when you do a macro model simulation, it is more of a reduced ordered model file. Okay, as I mentioned here in this case, where you get a HDL file as a black box and then feed that HDL file onto this black box, and then you can get output. The simulation of a reduced ordered model output happens less than a minute. Okay, less than a minute. So you can check even with ANSYS, they have a mod, they gave it a different name. Model, I think they have it in a different name. We call it as ROM, reduced ordered model. They have it in a different name. Okay, so in FEM simulation, ROM is recommended for faster simulations. Okay, so that is something where you can speed up the simulation output. Yeah.
Fine. So thank you. Thank you.
Okay. Okay. Yeah. So when we do the macro model simulation, where we have model extraction, strain energy and the model amplitudes, and then we have electrodes contributing to static analysis. The electrodes contribution, that is the metallization. Okay, and this is what we have here. And then we create all of these things, and then we have a simple. Okay. So here we have the macro model where MEMS elements. So we have this beams, combs, yeah, macro model template. So this macro model is for general MEMS devices. So for piezoelectric based models, we have piezoelectric based model. Okay, we can create a element like this, and then we can get the output. We can load the reduced ordered model file, and then we can do the simulation. So let me show you. So it gives a warning saying that 3D visualization is not possible in macro model simulation. That's okay. Okay, when we do element based model, we get 3D. On macro model, we don't get it. So we can connect a output, and then this is where we connect the output, and then we can feed the value as the input signal, frequency, and other things, and then this simulation happens less than a minute. Okay, so it also helps to verify the FEM model with Lagrangian model, that is the lumped model. Okay, yeah. So coming back to this. Okay, so results on charge potential. So when we do the simulation on a time scale, you can see on the right side, what you see is the input signal that is given, a sin omega t, and the output is the displacement versus time. So this is with sample, without sample, plotted on the same plot, we can see there is a shift that happens. Okay, so there is a displacement change that happens. So SAW device based on what sensing material, just like optical sensors work on the principle of most of them, at least most of them work on the principle of RI, refractive index, that many sensors can be built based on sensing the change in the refractive index. So here, by changing the sensing material, a specific application can be built. Okay, and with love waves and also on the Rayleigh waves, we can do the simulation using this tool. Okay, so while biosensing application, we hear a lot of micro heaters as a device. Gas sensing application. SAW device is also one of the prime device where we can use this to create a lot of chemical sensing. I would say generalize it as a chemical sensing based on liquid or gas. You can decide on to that. Okay. So as of now, this is what we have for specific to the SAW device. So I'm open for questions. So if you have any questions, you can ask me. Okay, I can show you how do we do other simulations also.
So for single user, license, what is the cost of this software?
Madam, for costing part of it, probably my colleague will be able to answer that. You can directly write to this email ID, india@intellisense.com. So my colleague would be able to give you that information.
So mail ID is provided, right? Okay, then I'll
yes,
mail.
you can see on the right side, india@intellisense.com.
Okay, sir. Thank you.
Yeah, please drop in an email. Okay, yeah.
Yeah, any other question? So
if anyone, this specific talk was on a SAW device, but there may be other MEMS users also. I mean, other people working in the other areas of MEMS. So maybe you can raise your query specific to that as well. Okay, it's not restricted only to surface acoustic wave device.
yes. The one question I can see in the chat box, Dr. Sonali Biswas.
Yes, sir.
Yeah, madam, you can unmute and you can ask directly.
Actually, answered this question. He is already.
Okay. Yes.
One more question I have actually.
Yes,
when we
please.
point load or like surface load, suppose it is for
Yes.
piezoresistive type of a sensor.
Yeah.
Like at first, like what should be the proper ideology? Like what is the type of load we should usually put at for the first time simulation, like before we see for the multiple number of load at different points?
Yeah. Okay. So let me, usually for piezo-resistive type of application, it is based on Wheatstone network principle. Okay. So if we are using it, typically we use, what we have an example as a pressure sensing application, which has also been proved at many places that we have PZ8, PZR. Yeah. So Wheatstone network principle. So first we try to simulate without the voltage, and then we have the simulation with voltage, and then we try to. I'm sorry. So first we don't define the input load, that is the pressure, and then further we simulate it with pressure and slowly gradually increase it to get the sensitivity value. Okay, that way you can see that. Let me open this example. Probably I think this is not the one. Yeah, so this is oriented to 110. Okay, so here what we define is piezo resistive This is the sequence of simulation settings. We define this is to be a piezoresistive material, and then we apply a face load, that is the surface load of, for this example, we have given 1 megapascal of pressure. Okay. When we define the piezoresistive material, we define the piezo pi coefficients. So in IntelliSuite, in the latest version, what we have as an advantage, earlier we had only this one, that we have to define the pi coefficients. But these pi coefficients are dependent on concentration of doping and process driven. If you are using a p type or an n type, so based on the ion type that you use, so you can set based on either by concentration, either by process driven. Okay, so based on this you can set the parameters for piezo resistors. In this case, the piezo resistors are the one which are turned red, and then we apply pressure onto it, we fix the boundary, we do the mesh, and we run the analysis. And further, for electrical simulation, we extract the resistor mesh and then we perform the electrical simulation. Yeah, so this is the sequence for any piezo resistive type of a device.
Thank you, sir. Thank you.
Any more question? Yeah, I think there is no question, no more question, Dr. Sripad. So you can continue.
Okay.
If you have some. Yeah.
Sure. Yeah. So one last thing that I would like to highlight here is that I want to show you that how this process model will really help in simulating a process driven model. Okay, that's where the novelty of IntelliSuite license. Probably I think I'll use this. Yes. Yes. Okay, so we have, when we create any process driven model, you can see that something like when we have a wet etching profile in the bottom, so we have to extract such profile onto the FEM simulation and then try to do the simulation. Okay, so such models will not be able to, it's not possible to create such models using 3D CAD models. Okay, so either we have to do a small 2D simulation onto this, but 3D is difficult to do, get such profile. And one other thing is that the wet etching profile is, when it is based on the experimental data, we can see that the orientation or the angle at which this wet etch profile is generated, the same model needs to be pushed to thermo-electromechanical module for simulation. So the same model is being pushed and then we see the output. So while you initially, when you do a 3D CAD model, directly designing without any process models, directly creating it and then simulating it is one aspect. But again, if you are very keen on fabricating the device, then what we recommend is that please try to simulate a process driven model also, so that you can get the output which are closer to your fabricated device. Okay, so that's extremely important. If you are not keen about fabricated device or trying to get an accurate model when you try to fabricate the device, then you are free to do a direct multiphysics simulation on the CAD model. But if you are very keen on to fabrication driven models, then you have to try to simulate such process driven models also. Yeah. So that's where the novelty of IntelliSuite lies in. Okay. while we have these multiphysics and system level simulation. So yeah, so I think I'm probably I'm done with whatever the content that I had. But in case if anyone has any more questions, I'm happy to answer them.
Yeah, thank you. Thank you, Dr. Sripad, for your nice presentation. And most important that this is the hands-on learning and training session. Though
Yes.
actually we could not make it in the physical mode, but obviously
Yes.
we have tried to make it in the online mode, and hopefully in the next upcoming events in the NIT Silchar, we can invite you and can request you to deliver one the offline mode, this kind of training session, so that the participants get immense benefit out of that.
Right. Okay. So here I'm dropping this message. India@intellisense.com is the email ID. So to make it more a hands-on session, the intended session was a hands-on. So to this email ID, if you can email us, those who are keen on getting a hands-on session, we can share a video tutorial of a SAW device, and we can give you access of the software for about 15 days. You can get the feel of the software, so that the intention of giving you a hands-on session is also complete.
So any questions? The last one or two questions maximum we can take before starting our next session. So if you want to ask any questions, we can take only one or two questions quickly. If you have, you can post in the chat box, or you can unmute yourself and can ask. So, okay, I think there is no such question, and you have shared your email ID. So I hope the participants, those who are interested to interact with you on these domains, they will surely contact you. So it's a one question now I can see in the chat box. Hello, Dr. Hari Kumar Naidu. Please, sir, you can unmute and can ask the question directly to the speaker.
Hello. Hello.
Yes, Dr. Hari Kumar.
Yes.
Yeah. See, nowadays, to save the people from accident, when the impact takes place during driving, the airbag is inflated, and it saves the human being, who is the driver, and even the occupants. So, are you doing any work on this?
Well, here we specifically on the device part of it, we are not working on it. Okay, but let me show you a video which is old video from the YouTube which I picked up. Okay, in that you can see how does that work. Basically, it is a gyroscope that works. So you can see this video. It's from Bosch gyroscope. So what we have, a gyroscope can be designed, and further the interface of those circuits can be done by any of the user. Okay, but this software can be used to build such applications. So this is a rotatory gyroscope. So the rate of change of capacitance in one direction changed. So that's where the sensing happens.
No, actually, what happens, that impact gives rise to the signal to open the airbag, and then that airbag protects a human being. You know, it will
Yes.
hold the neck, you know,
Yes.
his shoulders and all that. So that
Yes.
has come in market actually, and it is, and nowadays.
Yeah, it is already there. Yes.
Yeah, it's already there. So that is what I was, you know, thinking how it works actually.
Yes. Yeah. So this is how it works. Basically, so there is a very thin difference between an accelerometer and a gyroscope. Both are inertial device. Both measure vibration. The only difference that it has, gyroscope measures angular velocity. Accelerometer cannot measure angular velocity. That's all. If your accelerometer can measure angular velocity, it is not accelerometer, it is gyroscope. That's all.
Thank you. Thank you very much.
Yeah.
Hello.
Sir, yes, sir.
Dr.
Yeah. Yeah, Professor Raghavan, sir. Yes, sir.
Dr. Sripada Raj.
Dr. Raghavan, nice meeting you here, sir.
Can I? Very happy to. I enjoyed as usual your lectures, not lecture, practical one, including doubt clearance. You showed some video. One small controversial question I want to ask. If you like, you answer. Otherwise, you can answer in a different way. Can you please? You are the only person who can answer that question. Can you please list out the software available exclusively for BioMEMS? But I know
Specifically
IntelliSuite is the best.
No, sir, it depends. Like there are many softwares for BioMEMS. Let me not be biased to IntelliSuite. Thank you. You know, let me not be biased to IntelliSuite. Let me talk in terms of as a researcher. Let me talk in terms of a PhD student. Okay. So when we look at biosensing application, it depends on what is the mechanism. Basically, you also know that it's basically a mechanism.
BioMEMS.
Sir?
Yes.
Yeah, so based on the mechanism of operation, software can be used. If it is a SAW type of a sensor where it is a mechanical based approach, then if it is a micro heater, then if it is a SAW type of a device and or a resonant frequency change where cantilever beams are being used, any software can be used, either Coventerware or console or IntelliSuite. It's equally good. Okay, it's up to the user. When in terms of, there are biosensor applications where using optical methods. When we talk of optical methods, I think Coventer and IntelliSuite cannot play a role at all because there is no optical simulations that we can perform. If there is an optical facility provided by console or numerical softwares, it is very good. So numerical is extremely good in terms of biosensing application. So we have Dr. Venkatesh here, who is from Sai Vidya, who's done extensive work on that numerical software. Okay, so basically, I would say if we are talking in terms of MEMS devices as a biosensing application, all three are equally good. But if you are keen on the process-driven models and macro model simulation, I would say that IntelliSuite is good. Okay, because others have some dependencies on other softwares.
Very nice, very meteor.
Yeah, I think.
Only one small question, that with the permission of Dr. Guha. Can you hear me?
Yes, sir. Yes, sir. Please, sir, carry on. Sir, please.
Dr. Sripada Raj.
Yes, sir.
Sripada Raj, can you hear me?
Yeah, I can hear you, sir.
I know you ventured into BioMEMS in a form of hobby or with a special interest. That alone, can you please tell in front of the wonderful participants? What made you to get into BioMEMS?
Well, BioMEMS as such, well, my PhD area was on microfluidics.
You can do that.
No. No. Actually, to be technically talking onto that, here there are a lot of market opportunities on the biosensing application. To be honest and not be biased to anything else, let me be open to all that if you look at the funding agencies also, if there are anything related to healthcare, they are open to support. Okay. Hence, there are a lot of scope that have opened up in the last 2 years on the biosensing application. And incidentally, my work of PhD work is also on the microfluidics. Naturally, I have that tendency to work on the biosensing area.
Thanks a lot. Thanks.
Yeah, thank you, Dr.
Okay, yes, thank you so much. Now we can conclude this session.
Yes,
Ganraj. Hello.
Yes, sir.
Yes, you please conclude this session.
Thank you, sir. Thank you, Sripadraja, sir, for your insight towards whatever the challenges that are in the field of MEMS designing with a process-driven model, and if we are going with any Intel suite multiphysics simulations also. So, what are the challenges that we are facing? And I also thank you for giving an insight towards the application towards SAW-based microfluidic application. So that would be used in BioMEMS to say. Thank you for your gracious presence over here, sir. Thanks a lot.
Thank you, Gunnar.
Okay, now we can start. Oh, sir. Yeah, sir, start the session.
Okay. Welcome back to our 5-day FDP program on recent trends in BioMEMS and medical microdevices. We are pleased to have Dr. Anil Kumar with us today for the session. And before I give a brief introduction about Sir, I request Dr. Kaushik Guha to felicitate Dr. Anil Kumar, sir.
Yeah, so Dr. Anil Kumar. So kindly accept our virtual felicitation because we could not invite you and welcome you in the campus in physical mode due to the situation. So that's why, but at the same time, we would not miss the chance to felicitate our honorable speaker. So kindly accept our virtual felicitation. So with the very traditional Assamese gamocha. So thank you, sir, for
thank you very much
accepting our invitation and giving a valuable lecture on this session. Thank you, sir. Thanks a lot. Yeah, over to you, sir.
Thank you.
Okay.
Thank you.
So
Okay,
can I
I'll give a brief. Sir,
Yes,
I'll
sir.
give it just a
Yes,
brief.
you can share the screen. Just okay, you can share the screen.
Okay. Okay. By the time sir shares his screen, I would like to introduce our speaker, Dr. Anil Kumar. PR is a scientist specializing on cell technologies and biomedical applications. He is the head of the Division of Tissue Culture Biomedical Technology Wing, Sri Chitra Tirunal Institute for Medical Science and Technology, Kerala, India. He is also in charge of the 3D bioprinting facility and confocal microscopy facility. He has 17 years of research experience in cytotoxicity and cytocompatibility evaluation of biomaterials, bioengineering tissues, and development of bioreactors for tissue engineering. The main research areas include cell material interaction, stem cells, degradable scaffolds for skin regeneration, 3D bioprinting, and in vitro tissue models. Their lab is also working on developing new cell-based technology for testing biomedical devices. He has 45 research publications in peer-reviewed journals and 6 patents granted. He is also PhD guide and faculty for the courses MTech in Clinical Engineering and MPhil in Biomedical Technology. Dr. Anil Kumar is bestowed with various awards including Medi Biotech Award 2014, Young Bioengineer Award 2011, and Young Scientist Award 2005. He was honored with the DSG-IIPA Gold Medal in 2010 jointly by Indian Institute of Public Administration and Department of Science and Technology, Government of India. He is a fellow of Society for Education and Scientific Research, and life member of many national and state level societies. We are thankful for the opportunity to listen to his expert opinion on 3D printed microchips for cell technology. I would request sir to take over the session, please. Sir.
Thank you very much, Sonal. Can I share my slides now? Screen. Is it visible there?
Yes, sir.
So this is also a great opportunity for me to join you all for this faculty development program, and it's a very interesting topic. I extend my thanks to Dr. Guha, who has graciously very thankful to you, Dr. Guha, that we planned a conference on microfluidics before. Unfortunately, due to many other reasons, it was not possible. So he was a invited faculty there in that. Thank you all for having me here and share our little experience in the cell culture, 3D printed cell culture system, especially in the microfluidic platform. I think the audience is mainly engineers. Am I right? Or it's a mix of audience?
No, sir, it is a mix of audience, not the engineers. Yeah.
So partly yes, that's good. So my area of research here in Sri Chitra Tirunal Institute is on cytotoxicity and development of cultured cells for therapeutic application, especially in regeneration and all. There comes, being a cell culture lab, we are continuously exploring opportunities and feasibilities of finding new ways to test drugs, materials, and molecules. So, over the conventional two-dimensional culture system, our approach is to get into more in vivo-like. So this talk today will be based on that, how we get into, this is our entry into a continuous dynamic system. So with this small introduction, thankfully, thanks again to NIT Silchar for having me here. I just change my slide. Yep. So what is this microfluidic cell culture devices? These cell cultures are generally carried out in flask, petri dishes, and microdated plates. Multi-well plates like 96 well plate, 24 well plates, and for three-dimensional cultures, or in case of mass culture, we use bioreactors as well. In a culture medium to keep the cell viable and functional. In such cases, the cell is missing a lot of its environment, which is present in vivo. That is, the cell is missing its extracellular matrix. Extracellular matrix, or ECM, cell interaction is very essential to keep the functionalities of the cell. So mimicking those controlled cell responses to a particular stimuli in vitro is not so easy. No, it is not easy in a flask, in a bottle, or conventional systems. So there comes the microfluidics technologies. So cell-based assays have a potential to increase the biological relevance, when you use it as a cell culture model, and also for high throughput methods. For example, if I have, say, 10 drugs, I have to repeat I have a replicate of 6 numbers. Then I should have that much number of bottles in my incubator to do the test. So that is why people change to multi-well plates, 96 well plate. So you can have 96 samples in one small plate. You see, then if you further miniaturize your possibilities, it gets expanded. So that is why microfluidics are very popular in case of advanced technologies in cell culture systems. This cartoon represent the requirement and response of cell to the environment. Here in is my mouse pointer moving? Probably not. I think I have to take a.
No, sir, your pointer is moving, sir. We can see.
Oh, okay.
Moving.
So I think I will switch off that. Arrow would be next. Okay. So in this, the cells are here on the bottom, two cells, which interact with each other through cell receptor molecules or cell addition molecules, precisely. It also attached to the substratum. So there are two ways of communication to the cells. It attached to the substratum as well as it attached to another cell. Now, the cell, both of the cells, all the cells are exposed to a particular oxygen gradient. And as the cell grows inside this particular condition, the oxygen level comes down, like you see, from diagonally, from top left to bottom right. So as the oxygen level comes down, the cells are consuming oxygen for its life activities. So it increases the waste products, which is here. So gradually it is increasing the waste content. So the waste including the carbon dioxide. So the oxygen level comes down and carbon dioxide level increases with additional waste products like lactic acid or any other waste which is coming out of the cell or is released back. So this is a very kind of milieu which we cannot remove. In static culture, we have all these systems in the particular well. And when we apply certain pressure or a flow condition to this, now it is in a different mode. That means your waste products are removed continuously, new medium comes in. So that is why microfluidics have an advantage over conventional system. It is very complex, making miniaturized things. I was listening to the previous talk. It's so complex to me to even understand certain aspects, but it is very essential in case of nutrient transfer when we talk about cell culture. So we started with a simple design. Here we had a DST program on human on a chip. That means if we consume a tablet, then what occurs? It gets into the stomach, then intestine, it is absorbed, then it goes to the liver, and it goes to the heart, lung, and then come back to kidney and the rest of the body part, right, from the heart. So this is a flow of a molecule when we consume it. So similarly, we can have different cells from different tissues or representatives are from different tissues and make it into a microfluidic platform. So actually the fluidics part is micro. The cell we need in enormous amount. So what we have done is we have created cell culture chambers connected by microchannels. So this is the design, and we 3D printed it. The mold was 3D printed, and then we casted with the PDMS, polydimethyl siloxane. It's a elastomer, which is oxygen permeable. So when you culture cells there inside, and you cover it with a glass slide, still it can exchange gas efficient, but at the same time it is leak proof. So the channels is 400 micron only for the fluid. So here you can see a straight so here you can see a straight line serially arranged. We can put it in anywhere in very complex designs. So this is a very simple design. It shows that it is linearly connected, and then we have additional ports here to seed the cells. The cell will be seeded from this side. It goes there, and it will not overflow to either chamber. But when you perfuse fluid pass from one chamber to other sequentially. What I mean sequentially is when you start perfusing from this side, it fills in the chamber 1, then it goes to chamber 2, and 1 and 2 goes to chamber 3. It is very easy to say this. But you have to visualize that. Now you have to prove experimentally what I said is happening. So there are two ways that we can put cells into this system. That means we can seed cells in the form of a monolayer, or we can entrap into a gel and then put it inside the chamber, and the flow can be given. Once the flow is initiated, it goes in and then it goes out. So it's mix up. So if I have cells here, I intend only to change the medium, not the cells, right? That can be visualized here. Sorry. Yeah, I play here. It's not playing. Can I play the video separately? Exiting the PowerPoint.
Yes, sir. Yes, sir.
Yeah, I'm close that. I'm sorry. I'm stopping this for a while, if you don't mind. What's it? I don't know. I switched my computer. That's why. So that clearly shows okay. So now can you see the window?
Yes, sir.
So here, what you can see here is
the video isn't playing, sir. Yeah. It is.
Yeah. What we can see here is, I start again. It's from the bottom to the top in this case, for the red to the blue. So this is the portion where we, from the bottom side. So one chamber is filled with kind of a colored solution. The second one is filled with a blue colored solution. When you perfuse it, it passes from red to blue. The red occupies the blue, blue occupies the next chamber. So it is one after the other. Now this is not a perfect run. I can point out that there are a lot of bubbles coming in and out. So this is to visualize that the design works well, replacing the fluid from one chamber after the other. No, it is not just passing through all the chambers like we push a syringe piston. So yeah, you come back to the my slide. Okay. Here. So actually it is one after the other that the chamber. So this was our initial experiments to start with. Now this program is going on. We are connecting like intestinal cells, liver cells, and then lung and heart, so that we know that a molecule, when passed through different organ systems in vitro, how different cells behave. That is why it is called human on a chip. Then, yeah. Now we are, our main program is on liver toxicity testing. We are trying to develop biofabricated liver tissue. That means we use 3D printing technology, bioprinting technology, to print 3-dimensional liver constructs. I'm not talking on that. Why this 3D printed liver construct is essential? Because we have to have a functional liver construct in vitro, that means in cell culture, to test drugs. Why is it so important? because liver is a very complex organ and very specific fluid flow characteristics. It is not like through the blood vessel it passes. It's very complex inside the liver. The adverse effect of the chemicals and the drug, we study in vitro in two-dimensional culture system. It's not worthy to do that because it loses its functionality in culture. So liver cells are very functionally active cell than compared to other cell. Around some 3,000 biochemical reaction happens. Oh, I'm sorry. Happens in a second. So to mimic those kind of things in vitro is not so easy. You need viable cells first. Second, you need a perfusion system to remove all the waste, because it is highly metabolically active, means more and more waste. Oh, I'm sorry, I have to take this other call. Yep. Waste. So there are various ways that how the complexity can be brought into in vitro system. Instead of a monolayer, a layer of cell, it can be sandwiched in extracellular matrix. It can be made into a spheroid system. So, or it can be co-cultured with other cells. So these are various ways that you bring in function of liver in vitro. One of the best ways is to upgrade the two-dimensional system to three-dimensional, so that the cell will feel that it is in the liver, extracellular matrix. So it functions better than normal in 2D culture. So what we have done, we propose a design of a hepatic globule just to mimic the flow condition. So it is nothing to do with how you play with the cells. This talk is about how we make a perfusion system which can mimic the flow conditions in the liver. So this shows the importance of such kind of a hepatotoxicity system. In drug screening, it takes almost like 15 years to get a drug into market. So around some 10,000 molecules will be designed in silico, and then 250 formulations will be tested in preclinical, in animal studies. 5 will be screened out from the preclinical, and from the 5 clinical trials, this will go to clinical trials in human, and only 1 gets the approval of regulatory agencies. And most of the time, if you see FDA website, withdrawn drugs, most of the drug, more than 90% is getting rejected or withdrawn after it is launched into market. Why is this possible? No, every point it is FDA approval. That means it has gone through very stringent and strict regulatory screening approvals, and finally it is launched, and then after launching it is withdrawn. Why this happens? It happens because the physiology of a mouse or mice, which is normally done for the preclinical, is different from the human. So how can we address this? We can address this issue to reduce this kind of post-market withdrawal is by using human liver construct in the initial phase. For example, if 5 clinical trial drugs are identified, then we can test this in vitro again, go back and do an in vitro test with human cells and see the response and predict that among the 5, 1 or 2 might fail in human because it has got some sensitivity to human cells. So it is a prediction. It's not a confirmatory. None of the standard tests are replaced, but it will give an added value that the drug might go a bad response in humans. Why this complexity is so much? Because when you talk about liver is divided into lobes, and the lobes are divided into lobules. Each lobule has a very peculiar way of arranging the hepatocyte, and which is called the parenchymal cell, and non-parenchymal cells. That means other cells which support the hepatocyte to perform its function. Parenchymal and non-parenchymal cells are arranged in a particular way. So there will be flow conditions and all that. If you take this lobule, it is a hexagonal unit with 3 blood vessels, bile ductule, portal vein, and hepatic artery. So there, that means there are 3 vessels coming there: bile duct, portal vein, and a artery. Now at each corners of this hexagonal unit. So that means there are 3 vessels at each point. We call it as portal triads. So from the portal triad, from the portal triad, the blood flows into the central portion of the lobule, and from there it is pumped out. Okay, now this complex structure to mimic in vitro is very challenging. That means we need alternate in vitro system that can predict liver toxicity molecules to human cells. You know, the parameters that one would assess for this toxicity systems is the normal liver function test. That means that when we go and give a blood to a diagnostic center, you know, we check, you know, LDL, LDH, albumin, urea, VLDL, those kind of things. We check in the small liver constraint, no, or the in vitro system. Then we say that, okay, liver is functioning well, so the drug has this effect, good or bad. So that is how we do that. Now, what we have done is we have designed a liver lobule. So as I said, liver is in a hexagonal unit called lobules, and from the portal triad blood goes in, and from there it goes out, collected by the inferior vena cava to the heart. So we try to make this kind of design of a perfusion system. We cannot still call it as a bioreactor because it is only a chamber. So we call it as a perfusion device. So when it look like this from the top, so you have like a central vein, like similar, and from the portal triad, instead of 6 inlet, we have given 1 inlet, and inside the chamber it splits up into individual points. So this is something like it looked like from the bottom, and it was printed in the Stratasys Connect 2 3D printer. Now we use the printing powder, which is transparent, so that we can see the cells inside. So from the portal triad, the blood goes into the central vein and goes out. Now if you see these similar kind of things, it's like this. So from all sides it goes to the center, and then so in between the central vein and the hexagonal unit is filled with hepatocyte. Similarly, we will make the same arrangement here. So from all sides, the medium will flow, and we will have a cells encapsulated in a hydrogen and put it in each chamber, so that it mimics the conditions in the liver, flow condition. Now this design is now we analyze for the fluid flow condition. So finite element modeling was done with a hyper mesh. In LS Dyna, we outsource this facility, so that, you know, we get the analysis done. So there are 4 cases we studied, whether, you know, we made one 3D printed it, and whether the fluid is flowing as we wish. So we have to check that. So we did this analysis with the case 1 is the design which we have seen, and the case 2 is you know, inlet is from the bottom side and outlet from the other, so it radially fills in the chamber. Case 3 is it has 2 outlets, so that, you know, when you give an inlet, in the case 1, if you have an inlet 1 and outlet is in the center, so there will be pressure building up at the opposite side. To release that pressure, we put another outlet on the case 3 and then study. Case 4 is similar to case 1, but the distance between these portal triads, representing the portal triads, is different. So it is smaller here, on the other side it is. So with this, various flow conditions were simulated in silico to understand the fluid flow inside. So cell encapsulated 3D printed, or either encapsulated or 3D printed, will be placed inside this chambers here. So once you fill the cells inside the chamber, the device performs like a miniaturized disposable reactor, which is not at a stage that we call it as a bioreactor, but we intend to make a disposable bioreactor. You connect this and then throw it out, because it should be so cheap. Otherwise, microfluidic system is well known for past 25 years, but nobody use it. Even petri dishes and multiple plates and bottles are used. Why? It is a cutting edge, but it is not affordable. And it is not user friendly. So we try to make it very simple. These are the cases we study. Flow conditions like 4 microliter, 50 microliter, 100, 300, 500, and 1000. In all these cases, what we can find is 300 microliter per minute gave a good kind of fluid velocity inside when compared to the other systems. Now then we studied pressure distribution. Similarly, 300 and the 300 microliter per minute in the case 2 and case 4, that means the radial as well as this is and 4 microliter is omitted because the pressure pressure is very, very small there. But in 1000, we can see that from the 1000 microliter per minute flow rate, we could identify 2, like case 2 and case 4 as the good one. So this shows the simulation pressure distribution. So we can see that case 4 and case 2 is good. So mostly case 4. So our design is case 1. And how come this is? Because case 1 is the basic design that, I have shown you that image of our module, but case 4 is similar, but only thing is the difference in the portal triad entry, which will give a completely similar performance like another design. So we choose case 4 as our final thing. So pressure and velocity, if we compare case 2 and case 4 is good, but still in case 4 there is a accumulation of fluid without kind of exchange. But what we intend to see is the cells inside the chamber, so this is negligible to us. So case 4 is good without any further modification in the design. This shows the fluid flow condition. I think it can be seen small flow conditions here. So this is how we expect that the cells inside the chamber is nourished. Now we have 3D printed it. The first test would be a cytotoxicity test, whether the chamber we printed is toxic or non-toxic to cells. Then only we can use it for cell culture purpose. We did a direct contact test with L929 mouse fibroblast. We could see that the cells are very good and showing good morphology and all, like negative control, and positive control you can see at the extreme and C, which is very toxic. So the device is which is the 3D printed module. Now we need a medium to carry cells in the chamber. To hold the cells in the chamber, we need a matrix, which is an extracellular matrix. Otherwise, it is a monolayer again. We prepared a hydrogel. We call it as Gelma. It's a well-known polymer, which is a modified form of gelatin. So, metacrylated gelatin. Shall I continue? Or?
Yeah, Abhishek, you mute. Abhishek.
Okay. So something else. Somebody is talking to me, right? Yeah. Yeah. We need a medium to carry cells inside the chamber and hold it there and showing better performance. So the cells inside that lobule should feel that like it is the liver. So we prepared a hydrogel, which we called as Gelma. It's a well-known polymer, very well reported, widely used polymer. We also use the same. We prepared but ourselves here. It is a methacrylated form of gelatin. Gelatin is a good matrix to be used, but the problem is gelatin is soluble in water. So when you mix cells with the gelatin, it becomes thermosetting, but when you perfuse, the gelatin will be washed away. So what we have done is we methacrylated it. Once you methacrylate it, Gelma can cross-link. I mean, this molecule can cross-link in the form of porous matrix that you can see here. So the matrix is porous. You can have cells inside and put it in the flow device. You know, fluid will flow through these pores, and the cell will be nourished. We can see that, you know, over 7 days culture in this, and then we confirm it with NMR. There are two peaks here showing modification of this gelatin Gelma, and then we studied the rheological property, how it cross-links. You know, it is a photorheology work. That means, you know, the viscosity changes when you cross-link. So that was also done to see that, you know, the Gelma cross-link very well. Now, when you encapsulate cells, that is human hepatocyte cell line, HepG2 cells we used, and then we studied the cell activity, albumin and urea secretion. We found that over 7 days culture, you know, it is pretty good active when compared. It's normalized to normal culture, so it has got like 200 times, you know, 100 times more kind of live activity when compared to the another gel. It is not to monolayer, it's another gel. And then albumin and urea. In the Gelma hydrogel, we can see that the albumin synthesis increases over the time in the culture system. So this is all static culture, not perfusion or dynamic. It is static culture to say that our Gelma support hepatocyte growth. Now, the cell with Gelma will be put inside this chamber, and the inlet, through the inlet, the medium will be perfused so that it comes out, right? So in this, again, this is done static. We have not gone for perfusion in this work because we were lacking a perfusion pump for that. Okay, I will come to that later. So once the cells are encapsulated into these chambers and then we perfuse, we are expecting better performance. In a static culture, what we found was albumin and urea synthesis compared to a control monolayer and in the lobule, we could see that the function is maintained in the case of albumin and in urea. You can see that albumin in the lobule, it is less. It is not less actually, because in the lobule, it is inside the Gelma. So the albumin has to come out of the Gelma to get it measured. So that is why in monolayer, it is readily available in the culture. So that makes this difference. When you put it into a perfusion system, we expect that we will have a better function, much better than this. So we believe that the 3D printed lobule is a good kind of culture system to use it as a hepatotoxicity analysis. What we found was it is non-cytotoxic to cells. When we encapsulate Gelma inside and put it into the liver lobule, it expresses the liver specific function like albumin and urea. The flow conditions studied inside suggest there is a efficient fluid flow in the design 4. And in the next experiment, as I said, we were lacking a perfusion system. It is easy to say that, you know, we can have a microfluidic system, in vitro system to make. Now, there are practical difficulties. If I would say that you have a microfluidic system. How many pumps we have? No, we cannot conduct large number of, you know, all biological experiments require triplicate minimum. So in this kind of analysis, we need 6 numbers. So how we substantiate our data? You need 6 modules, separate modules, and 6 separate pumps, right? And all these things has to sit inside a carbon dioxide incubator. The pumps are not designed to sit inside a humidified atmosphere. No? Inside a carbon dioxide incubator, it's 95% relative humidity. The pump is not designed for that. So the pump has to sit outside and your module has to go inside. So these kind of complexities are there when you go from a 2-dimensional culture system to a microfluidic device. All the reports, I mean, all over the world currently available, you just go to PubMed and search, everything will say that, they have a good perfusion system, microfluidic system, but how you use it? So that is why these systems are not used. So we designed a pump that can sit inside the carbon dioxide incubator. It is very small. This, I think, 2-inch maybe, or 3-inch maximum at one side, and height is 7 centimeter to 12 centimeter roughly, 7 to 12, yeah, 7 centimeter height, and another 5 centimeter for the head unit. So it is very compact. It goes into the carbon dioxide, completely enclosed. We expect that there is only one motor which can function in the humidified atmosphere, and it can connect 6 separate microfluidic things with 6 separate inlet and 6 separate outlet. So this pump we decided specifically for connecting this microfluidic device. We haven't started experiment with this. This is again outsourced. Now we set the design and somebody made it for us. So this is what our experience with microfluidic cell culture system and the necessity of going for a 2-dimensional to 3-dimensional culture. I think I finished pretty fast, but I can go back and explain if anything is required. So this is our team. Dr. Shaini works on the JALMA, Rupesh work on the cell culture, Vinod work on the 3D printed modules.
Okay, sir.
Yep. I'm done with my slide, but any questions I can
yes,
address
sir,
now.
yes, yes. So yeah, so the panel is open for the question answers. So if any participants, if you want to ask something and interact with our speaker, please ask. Unmute yourself and can ask directly, or you can post your queries in the chat so that I can read the query also. So there is a good ample of time for interaction. So the speaker has finished the presentation part. Now there is a good time for interaction, I think. And the topics that you have presented, that is very, very interesting, and also money encourages some good interaction. So this is the good time to talk to you, to interact and to know the little bit more. Yeah, Satish, please. Hello. Yeah.
Yes, sir. Good afternoon, sir.
Good afternoon.
Sir, thank you very much, sir. I'm absolutely delighted to see that people are working on such kind of great technologies. This would be future. Presently, we can't say that this is a we can do some wonders and all, sir. But I have a question, sir. If you could answer it.
Yes, please.
How are you dealing with the turbulence which can rupture the cells?
Oh yeah. So we have a fluid analysis also when there are particles inside. We represent spheres inside, and then we simulate and see that how much pressure comes to that. That is one way to analyze that. Second, we are encapsulating cells and putting inside the chamber. So that means our fluid is passing, first hitting the gel, and then it is coming out. All the simulation is done with that condition. We have a porous matrix inside with a porosity of 80% and with a Darcy coefficient, and then we simulated all these studies. So what we see in the simulated data is what we expect to come as an outcome. So there is no turbulence expected inside. There is a velocity drop or a pressure increase is expected. Did I answer your question?
Sir, but yeah, sir, a bit, but I have another doubt, sir. So we know that at the walls of any chamber, at the walls, to the walls, though it is in at the level of micro level, and there is a possibility of turbulence. So because and another thing, sir. So the second question is, when there is a turbulence, there is a possibility of bubbles as well.
Oh,
so
yeah.
how are you with
Yes,
that?
yes. Actually, we started doing this microfluidic analysis with a review question, like you asked now.
Yeah.
That how are you trying to, because it is a micro channel, you are expecting micro bubbles there. So we haven't encountered any kind of problem with the cell function when we work on with this system. So that has to be separately studied. We haven't studied that, to be honest. Actually, whether the bubbles are formed inside the scaffold that we are giving, or it is like you said, it is at the walls that is forming, that has to be separately studied. We haven't gone to that level.
Oh, that's great,
But
sir.
it is a valid point. Yeah, one has to address those.
Yeah, it is valid, sir. Sir, another thing. So you are working on human primary kidneys, sorry, the liver cells, or only with the rat kidney cells?
A human cell line and rat primary hepatocyte, both we handle here, because the human cells are very expensive to purchase. For example, 4 million will cost us around some 80,000 rupees. So, and that will not divide also in culture. So it is, we are trying to get our own human cells in our next program. So we are collaborating with other local hospitals to get samples, and we isolate. Presently, we do rat hepatocyte primary isolated and human cell lines, human osteosarcoma, HepG2 cells.
Okay, sir. Sir, I always wonder about this. So if you are experienced enough, I suppose you can answer it, sir. Do you feel kidney? I mean, what these mouse cells do? What correctly replicate the human cells?
No. We have to do with human cells, at least cell line, not mouse or rat.
Okay, sir. Sir, how about the electrical properties you are dealing with? Does liver has any electrical properties kind of?
Not much. Liver is very peculiar that it switch off all its proliferating ability and it start complete function. Okay. So if you isolate hepatocyte from liver directly from the liver tissue, it will not divide because it is in its maximum possibility to divide. Function. Okay. That is the condition. So what we expect is human cells, when we take, that is the best cells to use. Oh, I'm sorry, otherwise this will disturb. Hello, Sanjit, I'm in a meeting. No. I'm sorry, otherwise they will call.
That's absolutely all right.
So I was telling that the best cells is hepatocyte primary.
Sir, so you are specifically working only on the diagnosis tools, or are you thinking of any implantable devices as well?
Oh yeah, we have both programs. In our 3D bioprinting program, we are trying to 3D print liver tissues with primary cells and then transplant. So that program is ongoing. So we got all the ethical approval now. Now, second, the parallel program is our hepatotoxicity test system. That is again 3D bioprinted. So we are getting customers now, which is open to as a test service. Now we are collaborating with industry to validate it, and our BioInc is going to be, technology transferred soon. So this is other work along with the toxicity system. 3D printed construct for transplantation and 3D printed construct for hepatotoxicity. These are two separate systems. But even if we 3D print a tissue, you need a flow device to make it nourished. So that is why we are parallelly doing a cell culture perfusion device. And that should be so cheap, not like expensive. If you buy a fluidic device from outside, it's very expensive.
Yes, sir,
nobody
true.
can afford that. So we are trying to develop a very cost efficient technology so that any local labs or small labs, I mean, ours are like a small lab. If you see, we have only 2-3 tissue culture rooms, nothing more than that. So we could afford that.
So, sir, final question. So with this, you must be targeting personalized diagnosis kind of, sir?
Multi-targeted? Sorry, I didn't hear that question.
You must be targeting at this personalized diagnosis tools.
Yeah. I mean, if the system is there, it could be personalized or general. Personalized means we take, patient-specific parameters. That is personalized kind of analysis.
Yes, sir.
For example, the cells could be from the patient, and you test 2-3 drugs. Second option is you have a common cell, but you take plasma from the patient and check that.
Okay.
So those kind of experiment, it is not done very routinely, but those are the approaches.
Yes, sir. Thank you very much, sir. Thank you for your patience in answering me, sir. Thank you.
Oh, thank you very much.
Excuse me, sir. This is Dr. Annie speaking.
Yes,
I
yes.
also have a doubt.
Yes,
sir, as you said, like definitely the guinea pigs and the mans never do give you the kind of results what you're expecting. You won't be getting that kind of similarity in the human beings.
Yes.
Right. So why we so much focus on that animal model? And at the same time, the cell culture also do have a problem like the immortality rate. Right.
Correct.
So that too also somewhere is going to create a problem.
Yes.
And later on, I have also been like going through this area. 3D modeling, animal modeling also has came in the picture. So is that the other previous two part is not that effective, the animal modeling and your cell culturing, or we have to either go to the 3D animal modeling structure? What is actually is the best to do the kind of work?
My slides are not. Oh yeah. So this is the scenario. Definitely, animals doesn't represent completely the human physiology. The list of drugs that is withdrawn, so far approved and withdrawn, is available in the FDA website, more than 90%. But why still? Again, FDA asked for animal experiment data. That's what we are telling, right, madam?
Yes, sir. Yes, sir. Why we do use the animal model then?
Yeah, because that is the only complete, validated, approved method that is available. If you see, some products are coming with a tag called not tested in animals. Right? There are a lot of cosmetic products coming as, and why this microfluidics test toxicity system is important. Some regulatory agencies banned animal experiments now. For cosmetic purpose, product evaluation, now animals cannot be used. Certain countries, European countries has got that ban already on animals, use of animals. It is over 8 years that is not shut down completely. It is over some years that you have to completely close this. So now attention is going to alternative methods to animal testing. Microfluidic system is one of such method. But if you ask me completely it will replace animal, I will not say yes. It cannot be, because animal will have a complete profile of systemic approach towards a drug or a molecule, whereas cell culture system will give you a cellular level approach. So I think a small amount of animal experiment has to be done. At the same time, you have to find out with alternative in vitro methods to find the relevance of that data and connect it to the clinical data. That is thing that we would follow, because we are also making hepatotoxicity test system. We don't believe that will completely replace animal experiment, because most of the regulatory agencies ask for that in vivo data. But we can add value to that data if we do a in vitro assay and say that, for example, see this, there are 5 drugs going to clinical trials, right? Before going to 5 drugs for clinical trial, which is a very expensive part of any drug screening method, the drug development method. Now, if we can do a human liver construct and do that 5 drug into a test in vitro and say that, okay, 2 or 3 might fail. That will save a lot of money for the company to invest, and that will eventually cut down the cost of the drug as well. So I would say a small amount of animal experiment should be there, even though it doesn't represent completely. At the same time, alternative method has to come up.
And what about the 3D animal cell project?
3D culture systems?
Yes. Yeah.
Oh yeah, we are working specifically on 3D bioprinted liver. We see possibilities in that, because when we compared monolayer with a 3D bioprinted construct, we found that cytochrome P450 activity is enormously high in 3D printed, whereas in monolayer it is low. It is less. So definitely 3D printed 3D culture represent better than monolayer.
Is it expensive too?
Actually, you know, the 3D construct is not expensive. The cells are expensive. So we have to find a, for example, roughly if I say, it won't add up much value than a normal kind of culture plate. You know, if your culture plate is 170 or 180 rupees, if you use 3D culture gel into that, it will add to like maybe 200, 300 maybe, or at maximum 500 rupees per plate. But you are getting 3-dimensional culture system there, which is not possible by normal routine culture methods, right? Actually, the cells and the analysis bioassays are expensive. If the albumin and urea assay which I showed, they're very expensive kits. It is not the culture system expensive. The analysis is expensive. So we are trying to make a perfusion system which can be, you know, which is affordable to a normal lab. Cell seeding, we you know, say that microfluidic system is very nice and it is high throughput and all those things. How do you seed cells into a microfluidic channel? It is a single channel, right? How do you localize cells inside? Addressing all those things, that is the design which I showed. Any lab, if you have a syringe and a needle, you can put cells into a chamber and it will stay there. It will not go to another chamber. To demonstrate that only, I have shown you that video. Medium will pass from one cell to other cell chamber. It just doesn't flow continuously from one to other. So 3D culture system, yes, we have to promote that. That is no, we are not culturing 3D you know, platform. Why? It's not available. It's all kind of, you know, commercial thing, right? We can buy plates, multiple plate. If somebody sells 3D, we will buy that. Yep.
Yes, sir. Yeah. I think one in the chat box I can see from Mahendran VS. Can you unmute yourself and can ask, please? Dr. Mahendran. Hello.
Yes, please, Mahendran.
So I can read out actually. So for in vitro assays of hepatotoxicity with cell cultures, what cell lines can be used? What are the parameters or analytes to be studied for synthetic secretory excretory functions of liver?
Yeah. We use Hep G2 cell, which is a human hepatosarcoma cell line, human cell line, which is approved by regulatory agencies in India also. CDSE also approves such kind of cells, analysis from such kind of cells. Second, what are the parameters? There are two sets of parameters. When you have hepatotoxicity in vitro platform, we consider it as two domains. One is you have to make sure that the construct perform like normal liver. Normal liver will give albumin and urea performance. So that is normal physiology. When the drug comes, it is not albumin and urea. It is the LDH, which is released when the cell is lysed, or cytochrome P450 to be precise. And there are many cell surface receptor molecules. For example, bile salt efflux protein, multi-drug resistant protein, MRP2, then apical polarity SDO1. There are various molecules in the list that we analyze separately for the drug evaluation and for the normal construct function evaluation. Did I answer, Mahendra?
Yes, sir. I think you have answered, but he's unable to unmute, and that's why he has texted in the chat box question. Yeah. So another question, sir, I can see that this is the last question of your session.
Yes.
Which type of FEM simulation tool have you used for analyzing the design?
Oh, if I have to say a particular name, I have to refer because we outsourced it, but I can get that. What software and what they have used, because it was done quite a long time back, maybe 3 years now. So all the modeling, the printing and analysis without cells was done quite a long time. We are now concentrating on the cell culture now. But yeah, if that information is secret, I can get back. Just give me a...
Okay, I think, sir, you have answered all the queries. Now we are over to Osar to conclude the session.
Yeah. It was a very good interaction. I mean, yeah, good.
Yes, yeah, fine. No, that's thanks to you for your time that I could contact you and I could get back to you. You have accepted my invitation.
Because we need a connectivity across India.
Yes, sir, yes, sir,
there are a lot of interesting scientists and researchers there, because nobody can single build all these kind of things.
Yes,
Different capabilities. Like I said, I don't know the fluidic part or the modeling part. There will be somebody who is expert in that. So actually, those kind of expertise should be connected and bring a device which is very novel, very user friendly. We in India, especially in all the DBT project, we make indigenous. Making cutting edge is one thing, and making it affordable is another thing. Making cutting edge needs a lot of investment. Making it affordable also need a lot of investment, but it will be affordable for all.
So the cost benefit analysis and economic analysis is also required.
Yes. We need a good network.
How much you invest? Yeah. What is the outcome, and how much is it affordable to all for common people or not? Obviously. Yes, sir. So I think, yeah, Osar, please conclude the session.
Okay.
Yes.
We thank Dr. Anil Kumar sir for a very interesting and session, showing us insight into the cell culture, how it can be mimicked into chips for use in the biomedical devices. We thank you, sir, for your time and patience for all the queries. Thank you, sir.
Thank you very much. Thanks.
Thank you, sir. Thank you.
Later.
Thanks. Thank you, sir. Sure, sir. So this is a standing invitation to you also. When the things will become normal, I will surely invite you to visit our campus. So please. Yeah.
I think there are also other minds in the interesting minds there. So hopefully we will all meet again in another conference.
Yes, sir. Sure, sir. Thank you.
Sri Chitra also.
Thank you, sir. Thank you very much.
What is the background of the audience? General background, majority?
Sir,
discipline?
Participants from engineering and some of the participants are from medical, pharmaceutical industries also.
Okay, engineering mostly what
Yes.
background? Which discipline?
Disciplines are electronics, biomedical engineering,
okay,
instrumentations.
You are in ECE, right?
Yes, sir. Yes, sir. I am in EC. In the NIT Silchar. Yeah, Anusha. Hello, Anusha. Are you connected? Are you present
Good
here?
afternoon, sir. Yes, sir.
Yeah,
Good
yeah.
afternoon.
Yes, sir. Good afternoon. So you can start now. Huh? We can start our session.
Okay,
Please.
sir. Good afternoon to one and all. I am Anusha Ellappu. A warm welcome to you to this informative program, Day 5, on recent trends in BioMEMS and medical micro devices, from devices to applications. So gear up, my dear students, members, organizers, for this cumulative learning and sharing experience. In today's session, our speaker, Professor G.K. Anant Suresh from IISc Bangalore. Before I give a brief introduction about Professor, I would like to invite our coordinator, Dr. Kaushik Guha, sir, for the felicitation. Sir, please.
Yes, yes. Actually, Professor Ananta Suresh, actually, we could not host the program in the physical mode, so that's why we have tried to virtually felicitate our speaker to kindly accept our virtual felicitation in this virtual mode. So thank you, sir, for accepting. So we want to felicitate with our very traditional Assamese gamocha and the flower bouquet. So thanks for you for accepting our invitation.
Thank you, sir. Thank you so much. GK sir Anand, GK sir earned his bachelor's degree from IIT Madras, master's from the University of Toledo, and PhD from the University of Michigan, and in all the mechanical engineering. His principal research interests are complaint mechanisms and topology optimization with applications in micro electromechanical systems, micromechanical of cells, biomedical devices, and micro robotics. In addition to research output, in terms of more than 275 journal and conference publications and 16 patents, his research group has spun off 4 startups. He currently serves as a professor and the chair of mechanical engineering at IISc. Thank you, sir. The stage is yours. Back to you, sir.
Thank you very much. Today I have some problems with the connection, internet. If anything goes off,
Yes,
just give me a couple of minutes and I would put it on a hotspot or something and come back. Okay. Yeah, I don't know why I'm appearing as 2 people here.
Yes, sir. Just now even I saw one is
Cisco gave me some trouble. Yeah, the WebEx. Okay. So let me just close one of those and then share the screen. Okay, there are 2 places. Okay, now one went away. No, it's still there.
No, sir. Still it is there.
Okay.
Better once you log off and log in again, sir.
Okay, I will do that. Yeah.
Okay, sir. We'll be waiting. Thank you, sir.
Okay. Now there is only one Ananta Suresh. Okay. Yeah.
Yes, sir.
So can you hear me now? And I will share my screen. So I'll stop my video.
Okay, sir.
Share the screen. Let me know when you see my screen. And it is full screen.
Yes,
Do you
sir.
see?
We can.
Yeah, you see my screen now? Okay.
Yes, sir.
Okay. Yeah, good afternoon. And I thank the organizers of this FDP program for inviting me for this to give this lecture. And I've chosen this title called Grasping Cells. So as you can see, I'm in mechanical engineering, but yet I work on biological cells. And that's probably not new today because a lot of people are working on biology problems. And so what the work that I'm going to describe is done with a number of my students as well as Professor Samitra Das, who is my colleague in microbiology and cell biology. So when a mechanical engineer does biology kind of work, we need a collaborator, and that is Professor Samitra Das for me here. A number of students who have now gone on to become faculty members in different places, and also industry. One of them has started a company also. Based on some of the things that I'm going to talk about, Santosh Bhargav has a company called Benflex and Spoom, and so they're doing something with the biomechanics. Okay, so now coming to the topic, when I say grasping cells, you can think of one meaning of the word, which is you're trying to grasp the sense of what the cells are. But for a mechanical engineer, grasping actually means quite literally holding a cell, grasping a cell and trying to see how it is. And that's what I'm going to talk about, both in terms of grasping, in terms of understanding cells, but also holding a cell and trying to analyze the mechanics of cell and try to figure out biology from there. Okay. So cells are basically, you can think of them as, you know, some people call it a drop of liquid, and some people call it a granular matter. There are a lot of things that are moving around inside a cell. It's very crowded. And in fact, to understand this crowded environment, it's actually good to look at how Francis Crick had described a biological cell. And how he described a biological cell? He said, if we were compelled to suggest a model for a biological cell, I would propose, he said, the mother's work basket, because there'll be a jumble of beads and buttons and threads of all shapes and sizes, and they're all jostling about, held together by colloidal forces. So Francis Crick defined a biological cell this way, which holds very aptly even now. And this was something he said in a 1950 paper. 1950 paper, where he said physical properties of cytoplasm. And there were two parts paper, and the first part was this, and the second part appeared also. So one of the things that he talks about in that paper is twisting a cell and dragging a cell and prodding a cell. So it's basically mechanically manipulating a biological cell to understand. And 1949, again, he had a paper before that, where again, he's talking about physical properties. The experimental one is a theory. And this 1949-50 is an important year because just 3 years after that, or 4 years after that, Crick and Watson discovered double helix structure. So it's actually very interesting that when they were looking at the molecular details of double helix DNA, he was also looking at mechanical properties of biological cells. So busy scientists are busy with many things. And over here, he had that quote that I just mentioned. And if you think 1949-50 is when people first start thinking about, that's wrong. So there are papers in 1926, 31, and 39. A lot of people thinking about physical properties of biological cells. Here it is erythrocytes, that is red blood cells. But people have been thinking about mechanical response of biological cells for a very long time. And in particular, if you look at this microscope, some of you would recognize whose microscope this was. This was actually Robert Hooke's, who first observed cork cells and gave the word cell to a biological cell, because there are compartments that he noticed. The same Robert Hooke, who lived in 17th century, he also gave this anagram in Latin, which means ut tensio seques, which is the fundamental law for mechanics people. The force varies as a stretch. That's what it means. And that's what today we call it Hooke's law of linear elasticity. So it was the same Robert Hooke who gave us cell biology and mechanics, deformation mechanics. It's very fundamental in both. And hence, the cell biology and mechanics of solids have been linked together since their birth, because both can be traced back to the same person. So today, when we talk about mechanics of cells or mechanics and cell biology, it is really nothing new. It was there right at the beginning. So what am I going to talk about? I'm going to talk about what we call mechanodiagnostics. Can we actually, not today, but with the further development, can we actually look at disease state of cells at the single cell level and using that mechanical techniques for that? Just like a doctor would feel the abdomen and then see whether everything is right about the patient or not. Similarly, we want to hold a cell as well and then see if everything is okay or not. So that is the diagnosis based on the mechanical response. And at the same time, would like to study, and a lot of people are studying, the effects of mechanical forces on biological cells, which people call mechanobiology. And in order to do these things, whether mechanodiagnostics or understanding biology from the mechanics perspective, you would need some mechanical interventions, and we need a lot of modeling, especially the inverse problems that I'm going to talk about. You need computation as well as experimental tools in order to do these two. And that's what we have done. So when you say mechanodiagnostics, just like, under the hood of the car, you look at various mechanical components, one can think about that doing a biological cell as well. That's what we mean by mechanodiagnostics. And why is it important? These biomechanical assays, because they provide an alternative to biochemical assays that we are used to today. We use a lot of chemicals and a lot of techniques that are there to assess how things are inside a cell or a group of cells. So can we do that using mechanical? And why do you want to do that? First is, it's going to be less expensive because we don't need any chemicals. Okay, for a doctor to palpate your abdomen, you don't need anything other than paying the doctor's fees. Similarly here, you just need to have mechanical tools using which you can assess. So it's going to be less expensive. And also small sample size, because we're doing it at a cell level. So you don't need a drop of blood, because that itself will have many, many cells. So we just need to have a few cells. And it will be very quick, because mechanical response, you squeeze something, you know what it is. So you're going to be very quick, and it will be very portable, because cells are very small. The device that holds that is also going to be very small. So it's going to be portable also. Probably quite economical too. But to get there, we have a lot of work to do, because specificity is very important in biology, because things are quite varied. That's what people think. And can we get that specificity? When you do this, the cell's mechanical response is different now compared to the normal one. So this is because of this disease condition. And that's where we'd like to go. So the outline of the talk is going to be, how do we measure mechanical response? What are the engineering tools that are necessary? We developed some tools. I'll describe them. And okay, you measure something, but how do you make sense out of it? So you need some modeling, computational techniques. I'm going to describe that as well. And with these engineering tools and computational techniques, how do you figure out any biological implication? Okay, you have biological assays that are done today. Now we have mechanical assays. How do you correlate them? I'll describe that with a couple of examples. And finally, if you want to change something in the cell behavior, you need more engineering tools to do that. That also I'll describe. So first, the tools and then the techniques. We manipulate cells in the sense that if you hold a ball in our hand, how would you manipulate the ball or a bottle or whatever? We tend to manipulate single biological cells in a suspended state in a similar way. And we have sensors for force, strain, stiffness. We have sensors for those that we have developed. And we also do cell culture outside the body, that is ex vivo, but imitating the in vivo conditions. So the way cell would grow inside a body, we'll have to create that environment outside. So it's not going to be simply petri dish culturing, but you have to do it in a 3D environment where there are forces to be applied and things to be sensed as well. Okay, so all of those tools is what we have developed, and the techniques. So there of course design of these tools, and you have to microfabricate them because biological cells are small. There are the micron dimensions. Your tools also have to be of that size. And then these inverse problems in mechanics that I'll describe, and continuum modeling and discrete element modeling. These are all the computational details. So we have both tools and the techniques. And I'll just describe our work using two examples. One is the drug efficacy in the case of breast cancer treatment, and other is biomechanics of hepatitis C virus and liver cells. Yeah. Okay. Anybody knows how to get rid of this? This doesn't seem to go. This top bar. Hello?
Hello, sir. Yeah, which one?
This top bar is blocking part of the screen. How do I get rid of it? I have to click on this, or what do I click to make sure that that goes? Do you see this at the top?
Yes.
But I don't want that. How do I get rid of that?
Top bar, actually. So, no, but we cannot see this one. So we are just only see the slides.
Oh, I see. Okay.
That's okay. We can only the slides only.
Okay, good. Yeah. So, so the tools that we use are what we call compliant mechanisms. They're of all different sizes. In fact, there is one tool that is relevant to this talk, which is this made of a photosensitive polymer, which is holding a breast cancer cell. Okay, these are the kinds of tools that I would describe. And how does it work? This is basically elastically deformable device. It is fixed over here and here. When I move this, these jaws will come together to hold something. And we can make this because it does not have any joints. This is one elastic continuum, one flexible structure. So it's going to deform at any scale. So we can make it very small. So these beams that you see, they can be of micron dimensions. So we can actually make something that is suitable for a biological cell. So with such tools, we can do all of these manipulations. We can grasp, we can squeeze, we can pierce, like injecting also can be done. We can roll. Okay, I'll show all this. We can peel a cell off. If it is a flat one, we can peel that and measure the peeling force. We can bend a cell, something that's flat. Corneocytes are flat. So there we can bend it. Also, we can probe, of course, like AFM and other things, we can probe as well. But we can also stretch a cell if you want. Okay, all of those things we can do. I'll show one by one the grasping. You notice if the video is playing, you can see that there is a breast cancer cell. Now this is zoomed in, and between the jaws, it is going to grasp. You will see. Yeah, you can see that we are grasping, and this thing is only a pipette just to position it between the jaws of the thing. We can grasp this way, and we can also squeeze it. I hope the video is playing. So it squeezes and it's recovering. It's actually real time. Okay, so I'll just play this one more time. So it would, yeah, squeezes and then comes back. And we can, of course, pierce it. You can see the it is held between the jaws of the gripper. Now we are kind of poking it and piercing. We can also inject. Some of here we have damaged it also. Okay, and we can roll it. So if you hold a cell with these jaws, we can also roll. You might ask, why do I need to roll? Right? This is all about mechanical response testing. You have to give some stimulus. If you roll it, you can hold it in different ways, and I'll explain why I need to do that. We can do this to single biological cells. And we can peel it also. This is a very special type of cell, corneocytes. We did it for a cosmetics company because they wanted to measure the peeling force when they have a new ointment or a cream, a face cream or skin cream. So how does it work? Instead of doing experiments on animals, you can do it on these things. So that's why we're trying to do this peeling. And we can bend also. That was done out of fun. Really nothing great here. But with the two tools that we are holding, it's more like micro robotic manipulation. We can actually bend it, as you will see. It'll be folded. Okay, this corneocyte is a flat cell, and now the video progresses. You can actually fold it like that. And of course, probing is very common. In fact, here we're probing with something, and we measure the force while probing also. It's very, very flexible. We can do that as well. And stretching is one of the most difficult things, where the cell is just suspended, trypsinized cell, and we want to hold it and then stretch it, not fixing anywhere. So here what we did was we have a little bigger tool. In that there is a smaller tool. This is done using microfabrication inside one. Outside one is made with 3D printing and other methods. So I'll just make a video, play a video of a macro scale thing that shows how we actually stretch it. So as the video would play, if I press here, these things are coming together. When they touch there, these things open up here. And that's where if you put a cell, or in this case, a rubber band will be kept there. We are pressing there, and rubber band, once these open up, when this and this touch, these things open. Now we can insert a piece of rubber band or a biological cell if it is small enough. And then we press again, it will actually stretch. So we can actually stretch a single biological cell, as you see here. Okay, and we have, of course, done this biological cell. I'll show the video later. This is just a macro scale prototype, all using this compliant mechanisms. And how do we roll it? Here is the simulation. Real device you saw close up where the cell was. Actually, this ball actually is rolling, and there are two actuations that are happening here. It's like holding in our hand and rolling, and we could do that also. These are all the tools that we have, and these are set up where we do all these manipulations. So what do we have? We have now an inverted microscope and a bunch of microcontrollers that control XYZ stages, and to which we have attached our small tools, miniature tools, and that will be operating or manipulating on biological cells. But we have another digital microscope camera here that measures the displacement, and from which we do calculations to measure the force also. Not only we are able to manipulate a biological cell in various ways, we also measure forces of those manipulations. Like if you hold a ball in our hand, you're applying some force to it. That force also we measure, and that's how our tools are set up. The details are, of course, in this paper. We are done long time ago, 2010. Okay, and before we proceed, I want you to think about, all of you may not be mechanical engineers, how flexible is a biological cell? So when you say flexible, if you apply certain magnitude of force, how much does it deform? Okay, like if you have a spring that is there in your ballpoint pen, if you hold this spring and apply certain amount of force to deflect it by certain displacement, okay, that gives you the stiffness. Okay, let's say this spring, if you want to compress it by 1 centimeter, let's assume that you apply 1 Newton force. It may be a few newtons, but let's say 1 Newton. So its stiffness is going to be 1 Newton per centimeter, or 100 newtons per meter. Okay, that means that you need to apply 1 Newton force to compress it by 1 centimeter. Okay, in this sense, if you ask how flexible or how stiff a biological cell is, and it'll be quite instructive to know that the cell stiffness is 0.001 Newton per meter on average on all cells if you consider. Okay, look at where 100 Newton per meter your ballpoint pen spring is and where this is. Okay, this is 1 lakh times smaller. Okay, and it's very, very flexible compared to some other molecules. The stiffness of a cell is much lower. Okay, and when we are holding a biological cell that is so flexible, so delicate, any amount of force that you apply going to damage it. So the challenge here is in designing and making these tools is to make these tools also have similar stiffness. Okay, let's say a robotic hand is there. You ask robotic hand to hold let's say a flower or egg, right? You just crumple the flower and break the egg, because if it doesn't know, the robotic gripper doesn't know, it's just going to squeeze it with applying a lot of force. So when we are manipulating that I showed, the critical thing there is, how do you make sure that the stiffness is matching with the stiffness of the cell? So you are gently manipulating the cell. Okay, you're holding and measuring the forces as well. And that's, I wanted to keep it. It's one of the most flexible things that we can work with. And for the stretching, of course, I said that there's a big mechanism, the smaller mechanism. The smaller mechanism has all these features, and these are made of SU8 polymer, and the size of it, if you see, this is 10 millimeters, and the little one has 1.7 to about 1.7, and these beams are of micron dimensions. They're very, very small. We use photolithography to make these things. And these are some of the images. So this scale bar is 500 microns. These are actually 5 microns or so. Very small, all these beams. And if you think that we are able to measure these forces and manipulate all that, again, that is also not new. Here is a 1939 paper which says the tension at the surface and other physical properties of the nucleated erythrocyte. Normally, as you know, the blood cells do not have a nucleus, but before they come into the circulation system, they would have a nucleus. So they are nucleated erythrocytes. And here, this paper used basically a simple fulcrum type of model, where they're putting this biological cell here, and there is a needle, and that is the fulcrum. And by moving that here, and they measure the displacement optically and try to arrive at the stiffness. So it's quite interesting that the stiffness that this paper, 1939 paper, gave is 1.4 dynes per centimeter, which is 0.0014 Newton units, Newton per meter. This is right on the dot. That's what I said. Cells have a stiffness of 0.001 Newton per meter. That's what they had given. So long ago, they were so right with the very crude instrument that they had. But even today, if you want to buy a tool that measures the stiffness, atomic force microscope is there, but that's not going to give you the stiffness. It's only going to probe on the surface of a cell and then see how stiff it is, right? That's one way. But holding a cell, try to find the stiffness, still you don't find anything. That's why we've developed these things. Okay, and they're all based on these compliant mechanisms. How if you apply a force at some point, this whole thing is elastic deformable. At some other point, it moves a lot. This moving a little, this moves a lot, and so is this. So if you apply a force here, this pointer is going to turn. And this is actually, yeah, I'm pushing here, that goes by a lot of distance. So we're using these amplification tools, and we can make them out of silicon, polymer SU8, and a lot of other things. Here also, compared to the motion of this thing here it's a lot more. So we use this mechanical amplification for these tools. And how do we measure forces? We measure the displacement of a few points. That's how you do in a spring balance, right? You have a spring, and if it is elongated by a certain distance, you take the distance, multiply the spring constant, you know what the force is. In a similar way, you measure the displacement of a few points and then compute the force that is being applied on the cell. And that's again described in these papers. So for that, we do what is called an inverse problem in elasticity, called Cauchy's problem, where we measure displacements at a few points where we can, and then we infer the forces at those points as well as other points as well. So it's a detail where we solve this mathematical equation and try to compute the forces based on measured displacement. Okay, so there is some portion where it may be fixed, our tool that is talking about, which will be in conjunction with the cell, and by measuring displacement of the miniature tool at a few points, which can be done very easily with microscopic measurements, we compute the forces everywhere. And using that, we have actually made a vision-based force sensor. So vision-based because the digital microscope is looking at a particular point on this pulse which is moving a lot when you apply force somewhere. Okay, this end effector here is the one that's going to be in contact with the cell, and we can measure that. And that's what we have done. Okay, with a biological cell, the displacement in microns, and this is like a calibration curve. And our tool is going to be what we call displacement amplifying compliant mechanism. This is the one that will come in touch with the cell. This is very small that we want to make. So we can, the stiffness of this is 2.6 Newton per meter, whereas cell is going to be 0.001 Newton per meter, right? So we have to be extremely careful using it, otherwise you could damage the cell. It's like poking a cell. So we made this compliant mechanism tools of various stiffnesses. So we have a resolution of 2 micronewtons of force, and the range is about 1 million Newton. And that's important because whatever force that you buy, if you say millinewton and smaller, they won't be able to, unless you go for atomic force microscope. Then they go very small forces. They go to nanonewtons and piconewtons and femtonewtons. Okay, in between is where the gap is. That's why we have developed this sense. Okay. Now coming to biomechanical assays. Okay, I would describe this with one case study, and this is where we look at MCF7, that's breast cancer cell line, and we subject this to multiple modes. So there is a compression test, there is a tension test, there is a shear test. Okay, this is how material scientists or materials engineers also characterize things. So 3 modes: tension, compression, and shear. Okay, that's what we are trying to do to these breast cancer cells to assess the drug efficacy. Okay, so here we have the control cells, and the blue is the nucleus, and red is actin, and the green is microtubules, all of them put together. Okay, and we treat that with 2 anti-cancer drugs, cytochalasin D and nocodazole. So what does cytochalasin D? It actually disrupts actin, and nocodazole disrupts microtubules. You can see that from here, the control to this, there is disruption. Okay? And this is, microtubules are disrupted with nocodazole. These are 2 anti-cancer drugs, and we'd like to see the efficacy of the drugs, meaning how much of this should be given, how much of this should be given, when this will be disrupted, this will be disrupted, and that we can sense mechanically. Okay, I'm seeing the questions that are being posed there. How do you know the tools will not break? Okay, we design them and make them in such a way that they don't break. Just like many other tools that you are using, okay, they are all not breaking because they're designed, they're engineered, and they're made with materials, suitable materials, so that they don't break. So you don't have to worry about that. We took care of it. Okay, and all these cells are going to be alive when we test them. So we need to make these tools sensitive enough so that they can handle the delicate. Okay. Whether you have warning system, yes. Whatever you do to normal engineering things, we can also do here. In fact, the company that I mentioned, my former student started, called Spuvum, they are trying to do this for assessing the, this is a fertility chip that they are doing. When you have egg cell that is fertilized, and after that, whether it is fertilized or not, you can assess mechanically. That's what this company is doing. Okay, when sperm enters and egg cell is fertilized, whether it is fertilized or not, you can assess mechanically. Okay, that it goes to that extent. I'm not going to talk about that application because that's commercial and the company is doing. Okay, but we are trying to do more biological studies. Okay, so first thing, when it comes to tension, we are using micropipette aspiration. How is it tension? Micropipette is a small glass tube. When the cell is sucked in, it's actually, you apply suction pressure here, it just goes in, as you see here. Okay, it just goes in. And if you apply more and more suction, it's going to get elongated into the tube. So that's like tension. Like stretching is one thing that I showed, but this is more easily done, micropipette aspiration. So that's what we did for these breast cancer cells. So the control has how much is the aspiration force, okay, or suction pressure. Pressure times the area of cross section gives us the force, nanonewton force. Okay, let's have around 50 nanonewton is what is for the normal MCF. the moment is subjected to cytokeratin D, which disrupts the actin, the suction force required for the same elongation has come down. Okay, and if you do nocodazole treatment, then that disrupts the microtubules. It suddenly becomes very small, so cell doesn't feel stiff at all anymore. Okay, because microtubules have been disrupted. Okay, and after that, after a while, effect of nocodazole goes away. It's going to come back up. So after a while, nocodazole treatment, but without that, if you do after a long time, it just comes back and recovers. Okay, so we have good correlation to see when it has the cytokeratin D and nocodazole treatment. So we can look at how much is the dosage by measuring the mechanical force, just to tell you how it is done. Okay, and now compression we can do with AFM, for example. You can also with our tool, but AFM is more readily accepted by people, so done with the atomic force microscope. So here we can assess the apparent modulus. It's not really Young's modulus, but apparent modulus of the cell. Okay, control is so much, about 350 or something like that Pascal. We could, if we subject it to cytokeratin D, that disrupts actin cortex, so that actually brings down the stiffness. And if you disrupt the nocodazole, it actually goes up. The reason it goes up is now instead of feeling the cell membrane stiffness, you feel the cell nucleus stiffness. Okay, because microtubules are all disrupted, you feel the nucleus stiffness. Nucleus is little stiffer than the cell membrane. Okay, it depends on, of course, how much actin is there. So that's why it's going up, and after that it is going to come back down. There's a lot of variability. We do with tens of cells here. Okay, and the shear. How do you create shear? For shear, we culture a cell in a microfluidic channel and then let the medium flow over it. Whenever something flows over something, we have the shear stress, and we can see what happens with that. There's control, and with cytokeratin D, there is more deformation because the actin is disrupted. Here, microtubule is just even more flexible, and then it comes back. Of course, it's recoverable with the nocodazole and not cytokeratin D. Okay, and so we have measured it using 3 different techniques and try to assess the mechanical response. So based on this, how much of this can be given to a particular patient, the cells are available, we could do. And that's the first thing for therapeutics. Now, so one more thing, right? So let's say that you have found that the stiffness is different for a biological cell. I'm just showing some images here, just as abstract images, either the cell membrane and then the cytoplasm and then the nuclear envelope and nucleoplasm. Let's say this is normal cell, this is abnormal or unhealthy cell. Something is wrong with it. Okay, so you do mechanical response of these various things we can do. We can do stiffness that I talked about, strength. What is the rupture strength? How much force do you apply to break the cell? Okay, and there is some stability also you can do. When does it buckle and things like that? When does it have wrinkles and things like that? Or viscoelastic behavior. So you hold a cell, squeeze it and remove the force. How long does it take for it to recover? You can measure that also. Or resonance frequency as well. If you vibrate it at some frequency where it matches its frequency, then it starts vibrating a lot more. Resonance, that also can be done. You can do all of these things. Okay, so but how do we tell them apart is the first question. Let's say applied that some force to a healthy cell, and I can determine the stiffness, and I can apply it to an unhealthy cell. Let's say it is stiffer. Let's say unhealthy cell is stiffer than the healthy cell. You determine. Okay, is that enough for diagnostics? No, right? Because it's stiffer, but that stiffness change could have happened due to many reasons. How do you specify a particular reason? So that specificity we try to decipher by asking the question, what changed the bulk stiffness? Okay, so let's say I have these 2 cells now, and if they have the same bulk stiffness also, okay, how do you tell them apart? Okay, because things are inside different, both of them feel the same stiffness. That could also happen. So how do you say what has happened? So for that, we do what is called the Dirichlet to Neumann map, which is to say how stiffness varies inside the cell. The cell is alive. We are holding a live cell, and we cannot damage it. Okay, it has to be kept alive, and we can only do it on the boundary. Just like imagine a doctor would palpate the abdomen or a leg or a limb or something. Okay, they palpate because they know, doctors know what a healthy one feels like and what something that is not healthy feels like. And the same thing we are doing and try to see what might have changed inside. And that is the mathematically what I've shown here. Dirichlet to Neumann map. By knowing the forces and displacements on the boundary, we try to infer what are the material properties inside. Okay, distribution is going to be inhomogeneous and so forth. Just to explain to you, we have taken some physical objects, 3D printed with a very soft material, and the second one, soft material, and there is a hard inclusion inside. Okay, if these are given, and you're asked to close your eyes, and only on the circular boundary you are allowed to apply, forces and feel. Okay, I'm sure you can tell the difference between the two. Because this feels stiffer. Okay, what caused the change in stiffness? What is what we would like to do that. There is this circular inclusion that is stiff. How do we do that? Here also, mechanical also uniqueness is a problem, and we have figured out how to establish this uniqueness. That is, if we are given, is all in the details in the paper. So if we are given these two kind of objects, when you hold in your hand, you have to hold them in multiple ways, lot of different ways, and then see how the stiffness is changing. And from there, you can figure out how is the distribution of elastic properties inside the cell. So you can tell whether nucleus has changed the stiffness, or cell membrane has changed stiffness, or some other organelle. So you can pinpoint it because we have microscopic images. We have this elastic mapping coming in. We can say what has caused the change in stiffness, and that's what we use our engineering tools and this. And now I'll describe the biological assays. Okay, and this work was done with Samitra Das and my former student Srinath Balakrishnan, who is now a faculty member at IIT Goa. So here we are working with hepatitis C virus infected liver cells, hepatocytes. These are only cell lines. The rest of the talk, whenever I show gray, it is HUH7, human hepatocyte cell line. And the second one, what I call replicant cells, they harbor HCV protein, non-structural protein. Structural things are removed and non-structurals are there, so they're not infectious that way. So, but they have all the properties of HCV affected cells. Okay, so these are HUH7 is control. This is our study cell. We take that and analyze it. So one of the first things that we noticed here was that if you look at HUH7 cell, this is the top view, and the green here refers to the nucleus, the stain, and this is the side view. This is another side view looking from this side. Okay, and HCV replicant cells, this is the top view, the side view, and the side view. Normally, when biologists look at this, they probably notice that on the average, and I'm showing only one cell, but you look at hundreds of cells or thousands of cells, and then looks like this nucleus looks a little bigger than nucleus in control. And not only that, the side view also, you see they're all scaled to the same way, 30 microns. This is very thickness, height of the cell when it is adhering to the substrate, okay, is much smaller than over here. Overall, when we noticed it, and as a mechanical people, we just look at it and say, why has the nucleus become bigger? Okay, and we want to know, bigger in the sense, top view it is bigger, what we call projected view is bigger, also height is bigger, the whole volume has changed. Okay, the nuclei of HCV replicant cell appear to have larger area and height. So we didn't leave that thought. For biology, it may not mean anything, but we want to know mechanically why is that. So nucleus is green and actin is red. Okay, so first we wanted to study this. When engineers study biological cells, we don't use the equipment that is there. Sometimes we actually build our own equipment. So here we did a bioreactor to culture these cells and look at them. It's perfusion, because we are working with liver cells, so perfusion is very much high in liver cells. So we made a perfusion bioreactor, miniature bioreactor. You can put your normal 24 well or 12 well things in here, and made a small miniature peristaltic pump. You can see our student holding it in his hand. You can see peristaltic pump. It's all done. So where we could do the perfusion bioreactor, and we could actually image the cells while they're growing. Live cell imaging can be done. Okay, and we can put multiple things, and we can do this recycling of these, or once a cell, this media flows over the cells, we can take it out and look at what is there in that medium also. Okay, and we can control the flow rate, and we did this at the physiological flow rate. Okay, now because we were using, and the company, my former student, actually has now a commercialized version of this. Okay, that they call cell chamber, perfusion enabled cell chamber, PECC. The Benflex does this. A lot of other people are also using this now. Okay, so one of the things is that when you look at all these nuclei, cell nuclei, we can get these images from confocal microscope, three-dimensional stacked images. Look at the top view. We can actually do some image processing to put a contour around the cells. So we take the cells, every one of them, I'm just showing here, but every one of them that is there with the image process, a lot of computation, we can actually compute what is the projected area. And then we have the confocal imaging. So we have stacked images. So we can actually see what is a volume as well. Okay, and there is an algorithm that we use for doing this thing for 2D as well as 3D. So 3D is there. So if I play this video, it just wraps around the whole cell, confocal images, top view, side views here, and does this. Okay. Yeah. So we can actually compute the volume. We can get the projected area. We can get the whole volume, and we can get the whole surface area also if you want. Okay, so all three geometric parameters, they're not nothing to biology here, just mechanical. We can compute the volume, surface area, and projected. Projected area is easy, top view, but you can get the surface area and volume also. So we did that, and then when we actually looked at it, so gray again is control, hepatocytes, and HCV, replicon cells, is the orange. Okay. Chamber size can be anything that because we are making it. We're not buying from anybody. We can make any size. So we can make 12 well, 24 well, whatever size you want, we can do that. Okay. All the details in our paper as well. So here we saw that projected area, okay, of the replicon cells was significantly higher than the control cells. So HUH7, we actually look at the number of cells. We have 461, 327, a lot of cells. Cell nuclei, sorry, it's not cell. Nuclei projected area is much larger. So it has become bigger. Second, this volume also has become bigger. As you can see, the distribution of control gray line and the red line, the volume also has increased. Whereas eccentricity has decreased. Okay, eccentricity meaning if it is approximately like an ellipse, 2a, 2b, right? Major axis and minor axis, and eccentricity is defined as square root of 1 minus b square by a square. That compared to the control, it has decreased. So things have become more rounded rather than being elliptical. So what do you make out of these? Right? These are mechanical observations. What do you make out? Okay, all we say is that HCV affected proteins, the HCV proteins that are there, they have increased the area and volume and decreased extent of the nucleus of hepatocytes. Okay, normally biologists probably wouldn't care about it, but we can think in terms of mechanical model. Okay, now what does it mean? So nucleus here is a green one. So you have the actin cortex, which is pushing down. Like this purple line is a substrate, cell is here, it is spread over, and this stretched membrane, cell membrane, is pushing the nucleus down. There is also osmotic pressure, the combined pressure. There's chromatin, osmotic pressure, microtubules. All these things are going to keep the nucleus inflated in some way, right? That net pressure is there, and then this F that comes from the actin. So you can imagine nucleus as a ball which is inflated, and we are pushing it down on the from top and bottom. Okay, so this model was done for tires, okay, automobile tires. The tires are also inflated. There is a weight of the vehicle going. That's where models are developed by mechanical engineers. Okay, and that's what we took that model and try to analyze what happens to something. So the internal pressure that keeps it inflated, initially spherical membrane, because anything that, because surface tension, everything is nucleus. If you just keep it outside, it will become a sphere, right? Now we are pressing it down. That's why cell nuclei will have those shapes. We took this model and did the simulation also. The inflated, if it is squeezed, it's going to become something else. Okay. Now we went and looked at this. Now, can we extract, if we know the HUH7 cells originally, what is the projected area, volume, and replicon cells, and we can infer indirectly. Okay, so how much force is there? 85 nanonewtons here, 100 nanonewtons here. Effective Young's modulus. We are making a lot of assumptions about the material properties. It's very heterogeneous, anisotropic, and all that. We are assuming simple material model, the 26 kPa and 13 kPa for HCV replicon. So what we find is that the increase in area and volume of the nucleus can be due to reduction in modulus of the nuclear envelope, and increase in pretension of the cortical actin of the cell. This is what we figured out from the mechanical model. Okay, so if we stop here, that will be just a mechanical study. So we want to go ahead and then see. And the cell count, we looked at as I shown in the previous one, right? So hundreds of cells, 400, 300, like that. So we did enough of those who are statistically significant observations we want to do there. Okay. So, and we also did AFM, and what we found out was this is a topography of HUH7, also HCP replicon cells. Okay, they're all, we have a live atomic force microscope, cell is still kept alive. Right. So what we found out here is that if we were to do force versus displacement, you're poking the cell, this is how it looks, okay, AFM. We found out that, again, cells, we have 21, 23, 34, 20. AFM experiment, each single cell takes quite a bit of time. So we cannot go to hundreds, but we went to tens, 20s and 30s, okay, or 40s. So here we found out that apparent model elasticity of replicon cells is actually higher than the control. Okay, and if we remove the actin using this cytokalasin D, then it actually comes down. Apparent modulus comes down. So we wanted to see what it means. So HCV proteins decrease the stiffness of the nucleus and marginally increase the stiffness of the cell. Okay, so here this is the entire cell. The cell stiffness has increased HCV. When you disrupt the actin, okay, it actually comes down. So nucleus stiffness has decreased, cell stiffness has increased. That's what we found out. The moment we say this, okay, HCV has the effect of decreasing the stiffness of the nucleus, my biology colleagues will jump and say, okay, what constitutes the nuclear envelope stiffness? They said, let's look at lamins. So we looked at lamin proteins. And what increases cell membrane stiffness is cortical actin. So we looked at cortical actin. So normally biologists would, if you want to pinpoint a particular protein, they would do a series of tests and then see what is upregulated, downregulated, and then see what. But here it's not like we are looking for it specifically. We know what's happening. Cell nuclear envelope stiffness is decreasing and cell membrane stiffness is increasing. So we can immediately go to molecular basis. We looked at lamin AC and then found out that yes, it is downregulated, and actin, cortical actin, is upregulated. And we did all the controls and negative and positive controls to confirm all this. We looked subject to different other viruses, Coxsackie virus and other things, and say that doesn't cause this effect, only HCV thing causes. So we looked at all this. Okay. So now, when we looked at this HUH7 and HCV plus this or replicon cells, we have now, when you just look at it overall, HUH7, HCV7, we can see that generally these nuclei are bigger, and we also see the actin expression is also more here. The red compared to here, it's more expression. And of course, we did that the normal biological assays. Okay, next thing we did was one more experiment. So now we know that lamin AC are downregulated. Okay, so this one can we explain? Yeah. So I'll be saying that lamin AC and beta actin expression is what we are looking at here. So this is the control is HUH7, and this one is our HUH7 with HCV-RA. What you see, the lamin, we have put AC here. It's very prominent. The nuclear envelope that we see is very prominent. Whereas HCV, it's not so prominent. It's down-regulated. Okay, so cell nucleus here has become more flexible, or at least nuclear envelope has become more flexible. Okay, and on the other hand, if you were to look at actin, you can see that actin is more, it's upregulated in HCV replicon cells. That's basically, I'm showing images. Previously, it was with gels. Okay. And now we try to do this with shear also. We cultured all these cells here. Now we are flowing medium over them, and then see how much of deformation, shear that occurs in these cells. Again, we did that with HUH7 and replicon cells. So here what we find is that after 72 hours and 120 hours, long experiment. Okay. So over here, we see that the eccentricity of the cells is changing. Okay. Again, the number of cells, since it's a flow, we can do thousands of cells. So complex with the experiment, sometimes with AFM, we can do tens of cells. With our tools, we can do hundreds of cells. And with microfluidics, you can do thousands of cells, because that's easy. Okay. What we want, the eccentricity of the nuclei of HCV replicon cells increases under physiological shear. And that's also consistent with our explanation. So this nucleus is there, that nuclear envelope has become more flexible. When you apply shear, it flexes more, it deflects more, the eccentricity increases. That's what we found out. Things were consistent. And the physiological shear stress of 0.1 millipascal is what we subjected. So with all of these things now, we want to see how heterogeneity in this whole thing, because if I have multiple cells, they're not going to be the same. We only look at average. Now how do you explain this heterogeneity? We were able to get the molecular basis, lamin AC are downregulated, which is important because our biology colleague, Professor Mitra said that, yeah, they had seen in HCV case, some proteins which are usually inside the nucleus are found outside. And then what is outside the nucleus are also found inside, meaning that the nuclear envelope has become more permeable. It's mechanically has become more flexible, but also permeable. So maybe just a speculation that HCV, what is virus mechanism of doing it is to make the nuclear envelope more permeable, so that things can go across and do its job. Those are the insights that we can get by looking at from mechanical. Next thing I want to talk about is cell heterogeneity. Right? If you look at these cells, okay, of course there are nuclei of the cells, and they're all of different sizes and shapes, highly heterogeneous. What do you make sense out of such things? So what we did is, by looking at projected area and the surface area and volume, all these nuclei that I explained already, we actually developed this model that I previously explained, that originally nucleus is a sphere, a ball, a sphere, and then actin, cortical actin would compress upon it, simplified model. And here we have this pressure P, actin force is F, and the nuclear envelope stiffness is E1. E1, we have some equations and non-dimensional parameters. We computed these parameters for all the nuclei that we have, lots and lots of nuclei. We found out that if we were to plot this, in a three-dimensional thing where there is normalized surface area and normalized projected area, normalized volume. Okay, all these things pretty much lie on a particular surface which you have fit with our mechanical model. In the sense, it's not fit to the data. It actually comes from mechanical model, which was there in the previous equation. There's a differential equation we solve, and from there we try to relate these surface area, projected area, and volume of deformed nucleus. All nuclei will be deformed like this. Originally, it's hypothetical. They are all balls, and then there is inflation that will be there, and of course there is this force that is coming in. So what is the projected area, volume, and surface area of this is what we have gotten experimentally, and the surface is the model, and it lies on that. Okay, there are two things here again. This is normal HPH7 control, and these red ones, orange ones are the replicon. Now we have more data where for different cell lines, actually, they all line up like this, but different things. We have a parameter for this axis and a parameter for this axis also. They all lie on the surface. Okay, and the shift here, you see the gray ones are over here, which is HUH7. They all moved. There is a reason for that. They have become bigger. What we call isometric scaling. Nuclei have become bigger. So whenever you see that, you know that something has changed. You don't need to do anything. You need to, anyway, you have microscope, you're looking at them without doing any biological assays, you know that something has changed. And we are able to do this for specific things. Okay. And we did AFM measurements also to see that stiffness has changed or not. We found it consistent. Okay. So with HU replicon cells, the cell thing goes away, and testing comes in later, is disrupted, so we have that as well. So all this heterogeneity, now we're able to understand from the mechanics viewpoint. So the main point here is that biology cannot escape physics. The mechanics is still intact, and we could do that. So let me just end at this point to say that we have means to measure the mechanical response and a lot of complex techniques, and we do the things. Then what more can we do? Mechanical intervention. So now that we are able to figure out biology in a few ways and cut down the biological studies, we can sometimes, as I showed, we can go to the molecular basis based on mechanical reasoning, so that you know which proteins to suspect. Okay, we're implicating the role of proteins in the mechanical response. There are more tools we can develop. Here is one of those which we call in situ cell stretching devices. All the microscope stage that we have, all that is for studies. That's not going to be a portable instrument. If you were to use inverted microscope in a clinical setting, that's not going to be viable, right? So even digital microscope, we have 4 sensor. That is fine. That's not going to cost a whole lot. We want to do more easier things. This is one of those which we call a cell stretcher. It's actually a small one. We are applying with the probe. This is 250 microns, right? There is this accordion type of thing, beam that moves. So we wanted to actually culture cells on top of this stretchable, what we call scaffolds, okay, and try to see how the cells would actually deform. So when we did that, so what you see here are these beams that can be stretched and contracted, like an accordion, okay, and the cells here we are imaging the nuclei of those because we are interested in nuclei. Okay, in situ stretching, we can do many of them at once with these devices. Not actuated, then actuated, it gets stretched, and we can compress. We can do all this. So here is a live video of one of those. What I'm showing here is those beams are there, and this is taken over a long time. Okay, it's like you can see it's gone to about 700 minutes. Okay, more than an hour, more than 2 hours, right? So we have done that, and image this. If you notice this, it actually detaches and then divides and then attaches again. So on the substrates, probably some of you would have seen that whenever cell divides, sometimes it detaches from the substrate, divides, and then attaches again. And we can measure the force. This is in micronewtons. The force comes down Okay, the time here, force comes down and then it goes up again. After it detaches, force comes down, attaches again there. What is that force? The force that the cell is applying on the device. So we wanted to make a cell structure where we culture cells and wanted to actuate them by pulling, pushing. But we found out that the stiffness of our device is so low, the cells themselves would apply force on it. They were stretching the thing themselves. That's what we found out here. Okay, so this is the kind of thing, no? 4 micronewton force comes down, reduction in force as one cell starts to detach from the device, and then it divides and then attaches again. So minimum force before it completely detaches, and then it goes up again. That we can see. So here is the cell, it's a nuclei, and then it about to detach and detached and kind of dividing. We can measure all these forces in real time. So multiple one of them. All we need to do is imaging. That can be done with very simple digital microscopes today, because we're not measuring displacement here, by the way. We are measuring far away. We're amplifying the displacement mechanically, as I explained earlier. Okay, so that is one thing. And second thing we're trying to do is in terms of the culture conditions. We make this, some people call them micro robots, micro rafts. So these are all, this is 500 microns, this scale bar here. We can make them with SU8 or PDMS. And these dots that you see, we embed magnetic nanoparticles in them. Why do you want to do that? Once you have a polymer filled with magnetic nanoparticles, you can apply magnetic fields and affect the forces, bring in the forces onto the thing. We can actually culture cells on top of these microrobots. Okay, as you can see, the blue here is for the nuclei of the cells. I think these are 3T3 cells, fibroblasts. Okay, we cultured on top of the SU8, which is compatible cells like them. They happily grow, and we can move them around. So there are cells grown here, and then microrobot has magnetic nanoparticles. From there, I can go there. I can culture 2 different cells and 2 different and bring them together. When I don't want to, I can take them apart. We can do all kinds of things. These mechanical manipulations with this cell culture, and that's something that's ongoing right now. So this video would show that when I apply magnetic field, how every one of them would dance the way we ask it to. So we can try to take them, and it can be used for various things. This now we are going towards, can we do this inside also, inside the organism if you want. Microrobots, we have the cells on top of them. They can move wherever and can do the different conditions. Now, if you see in this video, all of them are doing the same thing. All of them move that way, all of them move this way, all of them rotate. Okay. Now we are also trying to do with an array of coils. That was external magnetic field, bulk magnetic field, whereas this one shows individual coils here. So I can turn this. This is not turning at that time. So it depends on which coil that you activate. With an array of coils, localized fields, we can actually control the motion of each of these robots. Okay, and some of the coils here, we made it actually RR-CAT indoor, which has X-ray lithography. Dr. Vishal Dhamgai helped us make it, and we can make it very tiny coils. Okay, this is 500 microns. We can make it even smaller. The scale bar is 500 microns. We can make it much smaller. Electroplated gold here, where we did these things. Okay, microcoils. And when we do this, we have another thing. The forge that I showed was a single cell structure. We can do 3-dimensional as well. So here we make a thing that we're moving with a probe, but we find that the cells, when they're grown on it, they pull on these beams. This is like a spiral beam, and we know how much the spiral spring would deform. From there, we can compute what the force is. Once you know the force and displacement, you can infer the stiffness of the cell as well. So here's 2 nuclei you find, and a lot of them grown on this hexagonal packed spiral spring, so to speak. Okay, and other thing we do to create the in vivo environment for the cells, we have this electro-spun scaffolds. Into that, we put in magnetic nanoparticles. We can make them breathe. I hope the video is playing. It's actually breathing. The scaffold is now active, meaning we are making it move either out of plane or the right side thing. You can see that when the video plays, it's like contracting and expanding in plane. Okay, we can change the environment, because if you are studying lung cells or heart cells or gut cells, they're all in a dynamic environment where things are changing. We can create that as well. Okay, so we can actually, we have, of course, we have a lot of biology colleagues here who come up with interesting problems to use our tools, and that's what we're looking at: gut cells as well as lung cells. Okay? And so again, to summarize what we're doing, we can manipulate biological cells just like a doctor would do to your abdomen or something, right? We have these miniature tools, and I didn't explain the force sensing and strain and stiffness sensing in great detail because of diverse audience that we have today, but we have done all this. Okay, and we also can mimic. We have perfusion culture, three-dimensional culture. I didn't show much, but we can do. We are taking this active scaffold, so we can affect forces to change the cell environment. Whatever ECM you have, whatever ECM does, we can do that with our tools, and we can also measure the force applied by the cells. Okay, and all the design and everything I've not even gone into detail here, but there's a lot of computation also being. Okay? And two studies: drug efficacy in the case of breast cancer drugs. How much is the dosage that is right? We can mechanically assess, and that similar technique is now used. This POM company assessing the fertilization of the egg cells, and they can increase the yield in these fertility chips. Okay, what they call ICSI robot, intracytoplasmic sperm injection. Okay, that also they have improved the yield by using these tools and techniques. And also HCV is one case study that I told you about these liver cells. Okay. The main points is that mechanical response can be measured at the single cell level, and we can establish specificity also, and that paves the way for mechanodiagnostics. Of course, you can do PCR and all of this, right? But if you do mechanically, there's nothing like it. It's going to be much, much simpler, faster, cheaper, and more portable. Probably you can have it in your watch. Okay, so but then we have to do a lot of studies before we get there. I'm sure biochemical assays also did not come about, in 1 year or 10 years. It took a long time for them. Similarly, a lot more people are now working on mechanodiagnostics. It can get there. And we also try to understand the biological mechanisms, like I explained, using mechanical understanding. We can also intervene mechanically, as I showed, with the micro robots and active scaffolds and so forth. And sometimes mechanics aided insights are helpful, as I explained the case of liver cells that are affected with HCV. Okay? And there are a lot of students and a lot of funding agencies, of course, a lot of collaborators from different departments in IAAC. And this 3-element method, I'm not going to detail, but as I said, cell is a crowded environment with a lot of things moving around. We're using this 3-element method, which is a new method. My student just gave his colloquium. So I just will show one little video that related. This is something that mitochondria is squeezed by this M&M protein. Okay, it's like boa constrictors squeezing mitochondria, breaking into pieces. Okay, that we are trying to simulate. It's this. If I see something like that, I would say that life is very mechanical. Okay, so mechanics, what is there at the thing, now people are actually looking at it. We will also talk about mechanomics today, in the sense that you have mechanical markers, just like you have gene markers and other things, right? Now we have mechanical markers, so people talk about mechanomics. Okay, so I'll end here and take questions that you may have. Thank you. I'm glad my internet stayed on.
Yeah, thank you. Thank you,
Thank you,
Professor
sir. Thank you.
Ananta Suresh. It was a fantastic presentation, so I could not express. So I can see in the chat box also the people are very, very happy, and that however you have presented and a good correlation that between mechanical things, mechanosensory facts, and the mechanics with the biology, how the biologies can be combined with the mechanics, and how the mechanical people and all the other disciplinary people can work on the cell biology. So cell biology is not like that only the biology people can do. Also, we can invite some other people from other domains also to work on a novel and collaborative and innovative work. So it is clear from the lecture. So now this house is open for some queries, some question answers, or rather I would say it is some good interaction session. So if anybody want to ask,
Yes, sir.
Professor, yeah,
We
please
have
ask.
few.
Yeah.
Sir, can you hear me, sir?
Yes. Yeah.
Yes.
Sir, good afternoon, sir. I'm Satish. Sir, I know a very little about this cell. I mean, what is it, cell culture and all. So I have two basic questions, sir. Sir, regarding cell morphology, most of the times we consider elliptical shape or kind of circular shape and all. Does it affect oral performance and anything like that, sir?
Okay, it depends on the cell type, right? So when cell is on a substrate, it actually will not have circular elliptical, because focal adhesion points will be distributed. It will be more like, like cells that you see under microscope, right? I mean, they just basically will be like amoeba, if I may describe.
Yeah.
So it will stretch. Actually, cell, the moment it finds a good substrate, it actually stretches. Like we lie down on a bed, it also stretches. That's actually healthy sign. So earlier, when I started working my biology, they said these cells are very healthy. I asked to ask them, how do you tell? They say it's spread out a lot. It's so healthy. Okay, it is able to apply the force and pull on the substrate. Okay, at that time, nucleus actually gets compressed. When the cell membrane stretches like this, nucleus gets compressed. Okay, and those are the cues that we take mechanically. If you look at the morphology of the nucleus, also going to tell a lot. Okay, so that's how we look at these measurements. All cells are not of the same shape, but in vivo they have their, let's say, confluent cells. Even then you can see they squeeze one against the another, right? Then also nucleus also feels those forces and will have different morphology. The nucleus itself, shape of nucleus and size of the nucleus is going to tell a lot about what's happening inside the cell.
Okay, sir. Sir, then another question, sir. If I mean cell interaction and cell bonding, does it depend on the shape of the cells and all?
It's other way around. Based on the forces, the shape of the cell and nuclei will be changing.
Okay, sir.
Okay, mechanical forces control the integrity of the cell shape, right, and the nuclei, all organelle. Of course, nucleus doesn't have a particular shape. The mitochondria, some of those have shapes that you see in the books or papers, right? But here, anything that is not normal indicates that something else is happening there, and that's what we tend to get. Okay, a normal cell to a cell that is not normal, something would have changed inside, and that changes the overall shape and all the mechanical responses.
Yes, sir. Sir, simple another last question, sir. Sir, when we are done with cell culturing and we immobilize the things onto a substrate and all, so if a single cell dies, so do you consider it as a cancer cell kind of check? A dying of a cell is a cancer. So I'm just curious about that.
No. A cell in the lab can die for various reasons. There could be contamination. There could be medium is not right. So that we don't say. The cell, the death we don't consider here. We try to look at the live cell stiffness and other mechanical responses.
Okay, sir. Okay, sir. Thank you, sir.
Like to add that cell dying is the opposite of cancer. Cancer happens when cells don't die.
Yes, that's also true. They proliferate a lot, and that's what actually most of biology research depends on. All the cell lines are most of the cell lines are from cancerous cells. They proliferate, and that's why we're able to do all these tests.
Yeah. So, any more questions? So you can unmute yourself and can ask some few questions. We will take.
I am a doctor actually. I am an eye doctor, and I was wondering about usage of these pliant mechanisms in holding tissues such as the retina or the layers of the cornea for forceps kind of mechanism. Is that possible, sir?
Yes, yes, it is very much possible. We have not done that, but I have seen in the literature where people have done these compliant tools to hold it and do. Because your doctor, there's another, I mean, holding and making these tools for surgery, right? We are probably talking about in those conditions, how do you hold? It is possible. And there was another very interesting piece of work that I had come across. Instead of light actually activating retina, mechanical forces also can generate similar responses. Okay, in the people who are blind, there is a way to activate their optical nerves using mechanical stimulus given to the retina. So those are similar things are there. So that's why mechanics is now coming into the cell biology in many different ways. But surgical tools definitely, to hold eye is actually very accessible compared to liver or a heart or a lung. Yeah.
Thank you so much for the insight. Thank you, sir.
So any one or two questions? So we can take the last question maybe if we can ask. Or I could see one questions in the chat box, sir. So if you give me permission, I can read that question.
Sure, please. Yeah.
Sir, is it possible to measure the change in impedance due to the change in single cell characteristics?
Yeah. So what you call impedance in electrical terminology is what we call stiffness in some sense, right? That's what I showed. So single cell stiffness is what we can measure. Because electrically there will be impedance. Some people are doing electrical also, we're doing purely mechanical.
So there is an analogy between electrical and mechanical, the spring,
definitely,
and the resistance and this and that. Okay.
So just like I said, life is very mechanical. Electrical engineer might say life is very electrical.
Yes, sir. Yes, sir. I think, sir, you have answered all the queries. It's a wonderful presentation and explanation of all.
Hello.
Yes, sir. Hello.
I come to your lab many times. I am Dr. Raghavan.
Okay.
You also have come to my place. I got one basic question. You being a stalwart in mechanical, how did you go in deep in biological field, like tissue, all the things? Did you take extra course, or how did you develop there also this kind of expert system?
Okay. Actually, I don't think that I have understood biology a whole lot, but I have taken courses here. We have a bioengineering, department, biosystem science and engineering. So I and my colleague Sandhya Vishwesharaya, we set up that department. Now it is thriving with a lot of people doing a lot of fantastic bioengineering work. So I did sit in the biology courses, but I don't think I've become an expert. So I depend on my colleagues and who collaborate with me to do this. And my motivation, if you ask, it was actually quite simple. So I work on compliant devices, right? They're very flexible. And wherever flexible things are, I got interested. And I found out one day that biological cells are very flexible. So let me study. So that's how it came about.
Okay, thank you. Dr. Selvaraj and Vinay are my friends.
Oh, I see. Yeah.
Thank you. Very nice answer.
Thank
you. Okay, so I think we have reached at the end of the session. So I think now I would request Anusha to conclude the session.
Yes, sir. Thank you, sir. Thank you, sir, for this informative section about the grasping cells, microrafts, microrobotics, cell culture, etc. Thank you, sir. Thank you so much for having with us. Have a good day, sir. Thank you, sir.
Thank you. Thank you for your attention.
Thank you, sir. Thank you. Thank you for your time, sir. Thanks a lot. Thank you.
Bye. I log off now.
Yes, sir. Okay,
yes, sir.
Yeah, so the dear participants, now obviously that as per the mandate of ATAL, all the registered participants Yeah, Director sir. Good
afternoon, sir.
Sir, good afternoon. Yeah, Fazul sir, good afternoon.
Good afternoon, everybody. Yes, sir. Good afternoon.
Yes, sir. Good afternoon to all. Yeah. So I think Preeti, we can start because all the delegates already joined.
Honorable dignitaries, guests, and beloved participants. I, Preeti, on behalf of the Department of ECE and NIT Silchar, wish you a very good evening. It was raining in NIT Silchar. Now, the birds are chirping, the trees clapping, the ponds dripping, and the clear roads, as always, ready for the journey. We all have been associated for the past 5 days, and I believe this journey has added to one of the reliable pages of your book. On this note, I welcome you all to the valedictory function. I welcome you all, and on behalf of the Department of ECE, I'm very glad to welcome you for this valedictory function of the 5 days faculty development program on recent trends in BioMEMS and medical microdevices, from devices to applications, organized by the Department of ECE and NIT Silchar in collaboration with IEEE EDS Students Branch Chapter and IEEE Nanotechnology Council Chapter NIT Silchar, sponsored by AICTE Training and Learning Academy. Let me acknowledge the presence of our eminent dignitaries and guests who have graced this occasion. It's indeed our pleasure to have the Chief Patron of the workshop, Professor Shivaji Bandyopadhyay, Honorable Director, NIT Silchar. Welcome you, sir, and I thank you for your presence. I take this opportunity to welcome the Chairman of the workshop, Professor F.A. Talukdar, President IIC NIT Silchar. Thank you, sir, for your presence. With equal pleasure, I welcome the protagonist of the workshop, Dr. K.L. Vaishnav, HOD EC NIT Silchar. Thank you, sir, for your presence. I deem it my honor to welcome the man of great dignity and inspiration, honorable guest, Professor S. Raghavan, distinguished professor, NIT Trichy. Thank you, sir, for gracing the occasion. We have amongst us the convener of the workshop, Dr. Kaushik Guha, Assistant Professor of EC and Associate Dean Student Welfare, NIT Silchar. Welcome you, sir. A team is as strong as the one who leads it. I congratulate all the participants of the workshop for being here and for making it to the valedictory day. Now, I invite the convener of the workshop, Dr. Kaushik Guha, to give his speech.
Yeah. Thank you, Preeti. The Honorable Director, Professor Shivaji Bandyopadhyay, sir. The Honorable Chairman of the FDP, Professor F.A. Talukdar. The respected HOD, Head of the Department of Electronics and Communication Engineering, NIT Silchar, Dr. K.L. Vaishnav, sir. Our Honorable guest and also one of the eminent speaker of our FDP, Professor S. Raghavan, sir, also among us. So thank you, sir, for being all the sessions throughout the 5 days to be here. So it is my privilege to welcome you all in the valedictory session. So before moving to the next session, so just I want to present the brief report of the 5 days FDP. So far in the 5 days, what we have conducted, what we have shared with each other, who are the speakers, like that. So let me share the screen. Yeah, so actually, we have conducted the FDP, that is 5 days faculty development program on recent trends in MEMS and medical micro devices, from devices to applications. So during the 22 to 24 August in virtual mode. So the aim of this FDP actually was to bring the great minds in medicine industry and the academia together to enlighten and share their knowledge to work in such a interdisciplinary fields. And also it would provide a platform to interact with our experts from medical centers, IITs, NITs, and other reputed organizations, along with the participants from different institutes across the globe. So So again, I just want to share with you. So the committee members of that. So the committee member is already been, I think you know. So the entire EC family is there involved in conducting this successful program. So total 14 distinguished speakers actually we have taken, and they have agreed to deliver the lectures during the 5 days. Also, we have the 200 registered participants in our FDP. So we have organized the inauguration, the ceremony on the 20 August at 10 o'clock in the morning in the virtual mode. So this was the guest of our inaugural function. Our director sir was there. Then the chief guest was Padma Shri Dr. Ravi Kannan, the director of Kachar Cancer Hospital. Then he also graced the inaugural session. Then our guest of honor was Professor S. Raghavan, also is also now is present here from NIT Trichy. Then Dr. Pratim Shendukti is also one of the eminent speaker in this 5 days FDP. He also graced the inaugural session, which is present. So, and the other delegates who was present in the inaugural session, that our the Dean Faculty Welfare, Professor P.K. Patwari sir, the Dean Research and Consultancy NIT Silchar and patron of the FDP, Professor S. Boisho sir. So these are all the eminent speakers who have accepted our invitation, and they have agreed to deliver their talk from their busy schedule. So we have 14 eminent speakers we have, you can see. So now I'm coming to the session. The session was the first session in the FDP. Just I have given one talk on the kidney on chip, some overview and the research glance what NIT Silchar is doing on this field. We have started a very small thing, just new in this field, but we have shown that what we are doing in this field. Then the second session, it was delivered by very renowned man, very eminent person, Padma Shri Professor A.K. Roy sir. So he delivered the talk on molecular imaging and applications in disease diagnosis. It was a fantastic talk and fantastic presentation. All the participants are very happy and interacted with our speaker. Then the third session was offered by Professor Shantanu Bhattacharya from IIT Kanpur. He delivered the talk on the topic printable energy storage and powering the miniaturized devices. It was also a very informative session and very interesting session. So our participants also interacted with the speaker and immensely benefited out of his lecture. So in the second day, we have a talk by Professor K. Srinivasa Rao from Yale University. It was a long-term collaborator. We are working together in the MEMS field. Sir is also given a very nice talk, the technological advances in MEMS and medical MEMS domain. Then also as per the ATAL mandate, so we have organized one session for the mental health and stability. So the title of talk was Achieve Peace, Joy and Good Health through the Sahaja Yoga. So our speaker was Mr. Chandrakant Deora from Sahaja Yoga Meditation Group. He also given a wonderful lecture and session. All the participants were very interactive with him. So the session was also going very good, very charming. Then the session 6 was hosted by our also one of the very good speaker from foreign country, which is from University of TNT, Netherlands, Dr. R.P. Shukla. He also gave a very interesting talk on electrochemical microsystems for personalized medicine. So he has also given a lot of scope for collaborative research. He also expressed to work jointly, collaboratively. Also, all the participants are also very happy to interact with him. The next, the session 7, it was by Professor Devjani Paul Madam from IIT Bombay, very renowned accomplished researcher in the field of microfluidics. So she gave one talk on the paper fluidic devices for affordable healthcare. Very nice presentation, and she has actually shown us how very low cost type of microfluidic devices using the paper can be actually used for the healthcare application and point of care diagnosis. Very fantastic and highly interesting talk. The next session, session 8, was from Professor Ajay Agarwal from IIT Jodhpur. Sarah has also given a wonderful talk on MEMS technologies for biomedical applications. Then the session 9 was also delivered by the speaker, who is also the medical professional. The Dr. Pratim Sengupta, the senior consultant nephrologist. He gave a talk on drug-induced nephrotoxicity, what everyone must know. This is a very, I think, good, all the participants, and this title is actually very important for all of us to know. So Sir has explained all the kidneys and the problems, how the technology can help get rid of this type of medical problems. Then the session 10 was delivered by Professor Pasi Kallio from Finland, Tampere University. He is also very renowned researcher in the field of microfluidics and biomedical engineering. Sir has given a talk on microfluidics and the microsensors for organ-on-chip applications. Then Professor S. Raghavan sir hold the session 11. Sir has given a wonderful overview, a talk on the BioMEMS in the healthcare. So how the BioMEMS devices and BioMEMS research can help in the healthcare sector for the common people, and what are the facilities are available in our country, what actually the next generation researchers can access the facilities, how to develop the BioMEMS devices. So it was a wonderful session. Then sorry, actually, so the figure is actually the wrong. Actually, yeah, the session 12 was hosted by Dr. Rajiv Dey from NIT Silchar. He's from electrical engineering. So Dr. Dey has given a wonderful talk on artificial pancreas system, the role of computation and control. It is a completely different and offbeat type of topic, but still it is a very interesting and important for the collaboration, because we believe that not only that design and development of the biomedical device is important, but the control is also important. So the SAR has given a total how to control this type of systems, the biomedical systems. Then today morning, one hands-on training session we have arranged, and it was delivered by Dr. Sripad Raja from Intellisense Private Limited. So he has shown us some kind of design and development, some kind of BioMEMS devices in the IntelliSuite domain. So it was a very interactive hands-on learning session. Then after that, Dr. Anil Kumar PR from SCTI MST Kerala, Trivandrum. So Sir has given a talk on 3D printed microfluidic system for cell culture. Also, it was a nice experience to listen to him. So he's also a great researcher and scientist in the field of this the cell culture and the BioMEMS, the biology, cell biological devices. Then today's the last session. The last talk was Professor G.K. Anantasuresh, very renowned professor in our country from ISC Bangalore. So Sir has given a talk on the grasping cells. It was also one kind of wonderful blend of mechanics and mechanical engineering versus cell biology. Sir has given a new research domain, or the research avenue, how the mechanical engineers and other engineers, electronics, maybe electrical, how we can work together, and how we can work and contribute in the cell biology or the biological things. So it was also a very interesting session. So apart from this, so there is some FDP snapshots that I can present you. You can see some of these pictures, the snapshots that we have taken throughout these 5 days. So almost all the participants were filled up in the room. So all the participants have enjoyed all the sessions. After that, also as per the ATAL mandate, that we have conducted one test just before the valedictory session at 4 o'clock. So also all the participants have appeared the test. Thanks to all participants for appearing the test and cooperative class. So thank you all the participants and all the eminent speakers for joining us. So it would be our privilege for us to host all the eminent speakers and distinguished participants in our campus in our upcoming program when the current situation disperses away. So we are really looking forward to it. Now over to Preeti. Thank you.
Thank you, sir. Thank you for the brief report. Now it's my privilege to invite Professor Sivaji Bandyopadhyay, Honorable Director NIT Silchar to give his valuable words. Sir, please.
Very good evening to the distinguished delegates, my colleagues at NIT Silchar, all other participants in the today's valedictory program, and all those resource persons who have contributed during the 5 days of the faculty development program, and other participants who could not make it to the valedictory program as well. Now, in the valedictory program, we generally take stock of the situation, that is, with what objectives we started our journey, and when at the end of the 5-day program. So, what are the directions that we can identify? If we look into, we looked into, that is in the area of the research and the innovation. If we consider that that is our motivating factor in all our journey. So collaboration then is the main motto, because in today's interdisciplinary work, where every bit of activity, teaching, learning, and as well as research, they are interdisciplinary in nature. Internationalization is also another key factor, and industry as well as the faculties or the persons from the other domain, like say medicine or say surgery or etc. So with this, if you look back during this last that is the 5 days of the program, the experiences that were shared were of collaborations basically. And I understand that during the 5 days of the program, the young researchers must have identified the persons, the experts with whom they will be continuing their journey in the most collaborative manner. The interdisciplinary nature of the program of the area of BioMEMS and medical microdevices, I think that is already well identified and well understood. And based on the talks given by the experts that I was just looking into, so it ranges, that is what the term MEMS basically talks about. And so with the name itself is a interdisciplinary or a multidisciplinary one. And the talks were also identified in that way. And there were expert international speakers. And we understand that many of the young scholars who have started their work or who are in the midway of their journey, they must have identified that is the level of expertise that they can get from other experts. And without the networking being built and without your set of experiences being shared, I think organizing these kind of faculty development programs, that is the most important thing. And another thing I think we must have already noticed, that is those who are already faculties, and when they join such a course, so okay, they get up to date. But most important thing is that the PhD scholars who are basically the would-be faculties, that is who will be joining the faculty stream in future. So it is an eye-opener for them, that is in order to be a faculty, that is how interdisciplinary they need to know, how the networking they should be building on, and this kind of, that is when these ATAL FDP programs are held. So one of their motto is obviously, that is when you look into the objective of the success of an ATAL FDP, is that say how many participants are there, how many resource persons, how many from India, how many from abroad. I think if we look in the future, say how many collaborations have been newly developed after an FDP, how many new PhD registrations have been done, how many new research publications, patents have been carried out after an FDP was held. And that may be something like say 1 year, 2 years after. That is why in any such PhD or any such sharing of experiences, I always look into if someone is referring to some 1 year or 2 year before such workshops or seminars, conferences or FDP programs, and saying that, okay, from that I got the motivation to travel this further and to continue my journey for the future. So with this look for the present and for the future, and so I again express my thanks to all the participants. And I understand that from the feedback that we might be hearing from some of the participants, so these concepts will be echoed. Thank you.
Thank you, sir. Thank you very much for reminding us about the objectives and motivation of the workshop and talking about the collaboration and internationalization. Thank you very much, sir. Now I request the Professor F.A. Talukdar, sir, President IIC NIT Silchar, to deliver his speech. Sir, please.
Yeah, Preeti. Yeah, thank you, Preeti. Am I audible?
Yes, sir, clearly.
So, very good evening to everyone present. Professor Shivaji Bandapadhyay, Director NIT Silchar. Professor Raghavan is retired Professor ECG of NIT Trichy. Dr. K.L. Vaishnav, Head of the Department of Electronics and Communication Engineering, NIT Silchar. Dr. T.L. Lenka, Faculty Advisor, IEEE Students Branch and Nanotechnology, that means the Council Chapter at NIT Silchar. Dr. Kaushik Guha, the Coordinator of the event, distinguished guests, colleagues, delegates, graduate students, members of the media, ladies and gentlemen. On behalf of the Department of Electronics and Communication Engineering of NIT Silchar, IEEE EDS Students Branch, IEEE Nanotechnology Council Chapter, and Institutions Innovation Council, I welcome you all to the valedictory session of the 5-day webinar organized during 20 to 24th of August 2021. I am sure the event has considerably achieved its objectives and has opened possibilities of collaborative research in this most important area of electronics, biomedical engineering, and computing to improve the healthcare system. FDPs are curated programs, very similar to continuing education programs in medical and other professions, to familiarize the faculty in new and emerging areas, to hone and improve the skills of faculty so that they can meaningfully contribute to the teaching, learning, and research ecosystem. These are opportunities which enable one to listen to experts and decide their future for a meaningful achievement. A lot of thoughts and efforts are put in place by the host institute and AICT to conceptualize and implement an FDP. I congratulate the coordinator of the webinar for successfully conducting the program by pulling renowned experts from India and abroad. We sincerely appreciate the time and efforts of the expert resource persons for sharing their thoughts on BioMEMS and its applications and its potential in the overall healthcare system. I hope everyone has enjoyed this virtual congregation of frontline researchers in BioMEMS and derived benefits from the expert lectures and interactions and enriched your knowledge bank. Pandemic prevented us from showcasing our campus and facilities to all the delegates, expert speakers, and other dignitaries. We are assured that in future we will be able to host in person in our department. We look forward to your presence in our campus and the department at the earliest opportunity. We are open to collaboration in every possible variant to further the cause of research in electronics and communication engineering. We sincerely apologize for any lapses on our part in hosting and organizing the event. Such lapses are unintentional, and if you point it out, we will ensure that it is not repeated in future. Our Institute Startup Center will handhold any idea that may come out of the deliberations during the webinar. I urge upon all to explore and use our DITMISA facility. Looking forward meeting you DITMISA in future. Thank you all. Over to Preeti.
Thank you, sir. Thank you for your valuable speech. Now I'm pleased to welcome Dr. K.L. Vaishnav, HOD CA NIT Silchar, to give his valuable words. Sir, please.
Yeah, very good afternoon to all. Our Honorable Director, Sir Professor Shivaji Bandapadhyay. Then Professor F.A. Talukdar, Chairman of this workshop. Professor S. Raghavan, the speaker of this workshop, as well as honorable guest of this military function. Dr. Kaushik Guha, the convener of these workshops. Dr. T.L. Lenka, the advisor of IEEE Nano Electronics chapters, other esteemed colleagues, esteemed delegates, experts, and the participants, and my dear friends. We are extremely happy these 5 days, the way this expert really, 14 experts have given the deliberations in their own field. These all are really eye-opener for the many of us. And that could be another window where really there are many participants. I have seen that there are faculty, there are a good number of they are pursuing their PhD. There are a good number, maybe others programs. But these all the new domain that's that bio and electronics is a great really domain where we should work, because you see that totally our medical devices and equipments, we are basically depending upon on the other countries, Germans and other US countries, major items. German is really big, what is called big shot in this designing or manufacturing of this all sort of devices. I talked to one of my students who is now a PhD scholar in Denmark University. We observed that they are working on the live projects. So major equipment that we are recently getting to the India, basically from those countries. So we are really moving in the directions, because medical science and engineering, if you join together, really those days we can see also in India. So that's a really great honor to all the experts, because they are really working in their own domain and to the deeper extent. And I hope that this will enlighten many of us participants, faculty members, because they are maybe the ambassador for communicate. There are many faculties over there. Those are really that can communicate to the students, and that's the propaganda will be there, and this motivation to our next generations. So I'm extremely happy to the organizers, Dr. Koshigo, because judiciously has really picked up those experts. They have their own expertise in their own domain, and they have agreed to this to share the knowledge. That is also very important points. And already said that the main objective, not only the 5 days class, that workshops, whatever deliberation happen, main objective that's we should look for the collaborations. And that is the platforms where we can see so many faculty, so many PhD scholar. Today maybe you are PhD scholar, tomorrow you may be a great researcher. So that's really the opening here. We can have a great foundations, we can meet each other. Only because of COVID, not possible to physically meet each other, but days will come, hope so that days will come where we can meet each other again physically. But this is the starting point of journey that's really taken up this by Dr. Koshigo, that where we are so many people over here, around 200 participants in these workshops, and really the new chapter I'm expecting that India is moving in the directions of Atmanirbharship, where we can today and tomorrow we can see a day will come where we can have their own medical equipments at India. So with this objective, really, I'm extremely thankful to the all the experts for their great deliberation to these workshops. With this, and thank you the all, along with Dr. Koshigo, we have PT and Shorovs and Naushad. They are working really for the last couple of weeks, I believe, to the greater extent. And I'm extremely thankful to the all the team members of Dr. Koshigo, who are really in our family members, but they have given a lot of effort for the last couple of weeks. With this, thank you everyone for giving your valuable, because the participants are great important to workshop, because without participant, again, there's no meaning. So many experts are there, and who will be listening. So that's really great that you have also given your valuable time to listen those experts, and hope so that you will communicate to your next, and you will look forward for the greater collaboration from the near futures. With this, thank you everyone. Thank you to Dr. Koshigo. Thank you all. Over to Preeti.
Thank you, sir. Thank you for your valuable speech and sharing your thoughts with us. Now, it's my honor to welcome the most experienced and honorable guest, Professor X. Raghavan, Distinguished Professor, NIT Trichy, to share his valuable thoughts with us. Sir, please.
Valuable and lucky participants of the country, encouraging head of the department, Dr. Baishav, the real leader, Dr. Talukdar, the unique, unassuming, result-oriented director of all the 32 NITs. There is no time, otherwise I will tell how he used to interact even with the last grade staff member also. Anyway, let me tell about the FDP alone. Dr. Shivaji Bandapatiya. See, this it is not only the director is a unique person of all NITs. I mean it. I will elaborate some other time. This FDP itself is a unique one, and it's a role model. And at the time of 5 o'clock, the coordinator has given a colorful PowerPoint from the inaugural function till at 5 o'clock, including the test, except the result, all other things he has put it in the PowerPoint. That's a role model. Then Dr. Talukdar told about the pandemic. Nobody felt, and who really enjoyed is all those speakers. The offline reception was better. The online reception was much better than offline reception. That was itself unique. Nobody, it's not Raghavan who is telling, the nephrologist himself, the cancer hospital director himself, they all told how different this inaugural function was. That was the small indication how this 5-day session will go. And only I will take only 3-4 minutes. I just want to point out a few feedbacks. I shall put it in the Word. Now that he has put in a beautiful PowerPoint, let me at least list it out and send it to the coordinator so that that can be transmitted to the director and also to ATAL. Incidentally, the vice chairman was my hostel mate, Punya. Okay, the first one, the attendance remained constant every session. What is the speciality is even after uploading the attendance link, even after that people remained. That 100 or 98, that remained. Even now, almost 80 are there. So that is the first thing. That is because of the content. The second one, the questions posted by the participant are too good. One cannot decide that person belongs to a engineering field or a medical field. That is a unique thing. And third one, one of the participants is from DST Gurgaon. When every speaker starts, he used to verbally welcome, apart from MCs. Many things. I would like to know his name. Maybe during their feedback they will tell. I only know SSS Delta DST Gurgaon. He used to welcome every speaker at the start of the session. That is again a unique thing. And now I will come for the next uniqueness. See, normally in any engineering colleges, UG students used to think that they are the expert in MC work. But here are the 6 people who have exhibited and proven that they are nowhere inferior to the BTech students in MC work. And their MC work in my life I have not seen. It is not that just because I want to appreciate I am telling. Yesterday, that last speaker told the MC, please finish off your formalities. Instantaneously that MC told, sir, this is not a formality. This is also a routine thing. And that is what. One more thing, that credit may be going to the coordinator. Every MC while concluding, they used to tell all the important points of that session. So by that, he made all 6 MCs to listen carefully from the first word to the last word. So that is again a different from the MC's part. So that is what I told, encouraging head of the departments. Head of the department did not forget to mention any of the name of those 6 persons, Saurav, Satish, Preeti, Anusha, Naushad, would be doctorates. They will soon get doctorates, definitely, in the BioMEMS itself. So that is what I wanted to tell, uniqueness of the MCs. Then, as far as the speakers are concerned, anyone can take the definition of MEMS. So many people should join together. Then one more set of people should join for RF MEMS. Another set of people should join for BioMEMS. That grammar was physically shown by the handful picking up for the wonderful speakers, topmost speakers, last speaker, Ananda Suresh, his books play a big role throughout the world, practical person. Then morning, in that only I want to put a small request to the director through your HOD. Morning, there was a person from IntelliSuite. Then nephrologist came, urologist came, director of cancer institute came, industrial person who has not participated. Every branch, that is the grammar of MEMS, RF MEMS and BioMEMS. That is how the coordinator picked up the speakers. Then I have got only 2 more things to tell. Including the test, the last test to what he has conducted, I have seen in the chat box also, some of the questions have got wrong answers. Why they have come to that conclusion is, in the internet, what is available as answer, the coordinators put in the opposite way. So if they have anyone has blindly copied, they would have given wrong answers only. So including the test, it is different. And what all I want to request the coordinator is, please take out the printout of the chat box messages from the first day till the last day. That 100 messages will tell everyone how this FDP is totally different. That message printout you should definitely give to your director and also send it to ATAL. So many, this is not my word, these are all the words of the participants. So many FDPs are being conducted, more than 400. I am sure that none of the FDP would have been like this because of really interdisciplinary, multidisciplinary, everything, which the medical college would not have brought the engineers. Engineering institute would have brought this many doctors. That way, it is the unique. My last sentence is, I know many people know about the word of Shivakira. The Shivakira word is, winners don't do different things, but they do the same thing in a different way. There is no need that whom I am mentioning. All the participants in their field will definitely say what I am re-quoting from Shivakara definitely belong to Dr. Kaushik Guha and also the whole team stayed by Dr. Talukdar and the HOD. Okay, one request to the wonderful director. I really mean wonderful director. There are some directors who got scoldings also from me. I do not know whether it has already happened. See, INUP Bombay, INUP Bangalore are known throughout the world. Likewise, Dr. Kaushik Guha, with the support of the HODs, 2 HODs, ex-HOD, present HOD, he has proved that this group has got all the ability to have a wonderful BioMEMS center. So definitely, even though director has got mind, there are some methods, protocol and other things. So instead of waiting for 3, 4, 5 crores, I do not know whether you already started. You please start with a small software, you buy it. Like morning, Pandey is one of the expert in BioMEMS. You start from IntelliSuite, MEMSCAP, CoVentor. In that case, some more researches will come. Definitely, NIR of rank will go to the topmost. More researchers will come, lot of the outcomes. Another thing what I find in your researches is the outcome are not simply for journal papers, it is all for real societal value. And that I came to know through Dr. Talunda. He only told Dr. Kaushik Guha went around the country and wherever there is opportunity, facility, he made use of. Now it is your group should see that all the country people come to Silchar. That much facility you should create, and I know that your core people will do it, and in that case, it will be a milestone. And I'm telling you, I know all the NITs. It is not existing. This much work, even without much facility, real fabrication, other facility, you attain that. So that is what I want. You start from the smaller one, finish up all the software. That way you can go ahead. And I am sure that the person who has achieved, there are many uniqueness. Nowhere, no NIT has got this much big library. It is not even called library. It is called a knowledge center. So that way there are many uniqueness of your NIT Silchar. Now, if you do that, the telemedicine department will remove that telemedicine center from Nigris of Shillong, only because the facility is not existing. The Northeast people want this kind of telemedicine. If you start existing, I know that many doctors are willing to act with your department. I think while I was mentioning the 6 people, I think I forgotten to mention Satish also. Satish is simply playing with the nephrologist. So I congratulate along with the HOD all the 6 MCs for their wonderful coordination. And I am sure that the India and world will see how quickly the BioMEMS Center Excellence grows in the ECE department. I wish and very humbly request the director to tell one sentence at least in principle about the acceptance of my request. With this, I should thank the whole organizers. For 3 months, the coordinator would not have slept. Today also, he will not sleep because of the over satisfaction and joy. Whatever I told, nothing is exaggeration. It is true and true only. That will be reflected if you take the printout of the chat box messages. I know that many of the valuable participants also will tell their real feedback so that the powerful person of your institute should know from the third person what has happened in these 5 days. Thanks a lot. One minute, director's voice.
Yeah. So, Professor Raghavan, it is always a pleasure for us to listen to you and get ourselves motivated at each and every point. When I listen to you, listen to your presence or talks at other places, and definitely the kind of praise that you have showered on my, we try to be worthy of, and definitely your suggestion that NIT Silchar established as a center of excellence in BioMEMS and medical microdevices. I think we'll definitely be looking into it. And I understand that, okay, that is building a large scale thing requires large amount of money, but everything starts from a seed. And whatever you sow, you reap that. And I believe that all of us will be working towards the goal of sharing our experiences with all over India and across the globe also. Thank you, sir.
One small sentence. The NIT Silchar Associate and National Coordinator, Vice Chancellor Padma Shri, Dr. A.K. Ray also will support all my views because he was also a speaker, even though he was a purely ordinary image processing person. He has turned out to be a biological microwave imaging person. So you need a person in the national level, AK now will support in drafting. Thanks a lot.
Thank you.
Thank you, sir. Thank you very much for your valuable words and for having noticed and appreciating the highest and the minutest details also. Thank you for traveling with us in our dreams and for energizing and encouraging us through it. And thank you, Director Sir, for your words of assurance. Now, I hope the 5-day FDP has actually given great memories to the lives of the participants, and we would like to know how well we had our efforts transferred and resonated to you. Therefore, I request anyone from the participants to give their valuable feedback. Please unmute yourself and kindly give your valuable feedback. Yes, please. Someone has raised their hand. Please unmute yourself and you can speak, please.
Hello.
Yes, sir, we can hear you clear.
Good evening.
Malik, sir.
Good evening to all of you. My name is Amir Malik. I'm from J&K, Kashmir. Hello.
Sir, we can hear you clearly, sir. Yeah, please
Good
go ahead.
evening to all of you. My name is Amir Malik. I'm from J&K, Kashmir. I'm working as an vocational trainer here in a government school. Well, regarding this workshop, it was very fruitful present all these 5 days. This is my first time experience having attended such workshop. I thank you, the director of this NIT and Mr. Kaushik, who invited me for all this. I really enjoyed all. Well, this was the medical background field, so I got the knowledge from the engineering point of view, as the sir already told. In future, I would like to attend more workshops with you people. It was a great experience. And if in future you need my help, I can be available as a resource person for the workshops you may attend related to IT sector. Thank you. You can contact me on my mail or the phone number which I have shared with Mr. Kaushik, so we can be in touch on that. Thank you.
Sure. Thank you. Thanks a lot.
Thank you, Malik, sir. And we'll invite some more participants to give the valuable feedback, please.
Yes, ma'am. I would like to speak a few words, ma'am.
Yes, Satish, go ahead.
First of all, I'm just Satish. I just would like to introduce to everyone. The workshop has been.
Make your camera on, Satish. People like to see you. Satish.
Yeah. Sorry, sir. My appearance is not that appealing. I'm sorry for that, sir.
Okay.
The thing is, sir, I have been working with Dr. Kaushik Guha for since long time. So the talks you can see, every speaker over there is exactly what associated to the name of the workshop. It is very well tailored workshop, and the speakers, maybe the participants may not be knowing that speakers are one of the busiest persons in India. I personally know them. And I don't know how we got them, how we captured them. Eventually, they gave a talk, and it is the future is in this MEMS, and the future is in this microfluidic cell culturing and all. So people after listening to such talks, they will fall into this category, and they will be interested in researching in such things. And if any people interested in it, you can directly contact Dr. Kaushik Guha. He is someone who is always interested in collaborations and all. So we are also working in the same area. So we'll be inviting such kind of collaborations. So thank you, participants, all of you. Hope you enjoyed the sessions and all.
Thank you, Satish. Anyone from the participants, please go ahead to give your feedback. Yeah, please, ma'am. Ma'am, can you kindly unmute yourself? We can't hear you.
Oh, sorry. Can you hear me now?
Yeah, now. Please go ahead.
Yeah, I am Tasneem. I am from Kerala. I am working as assistant professor in College of Engineering, Periman. I felt that the all the topics was on a bit advanced level, And it was nice hearing all the speakers, and each and every minute was not a waste, I could say. Each and every minute was useful, and it was a wonderful program, and we could gather lots of knowledge, and very happy about that, except about the exams. Sorry to say that. And also hearty congratulations to the organizers, Kaushik sir, Preeti and Anusha, for the wonderful organization. Could have seen through the speakers that how much pain you have took to arrange this wonderful program, getting so much good speakers. Very nice attending this program. Thank you.
Thank you, ma'am. Yeah, I can see SSS ARCI ID trying to reach us through voice, but he says he's not able to. So kindly, sir, try to unmute yourself or see at your end, or kindly type something in the chat, and I can read out that for you. Anyone else in the meanwhile can please go ahead and speak.
Ma'am, my voice is audible?
Yes, sir.
Is it audible?
Lakshmi Narayana, sir. Yes, sir, it's audible, please.
Yes, ma'am. Okay, I'm very happy to share my views on this 5 days FDP on BioMEMS. Actually, my research area is on MEMS. I am doing an RF MEMS switch. Now I am looking to extend my research in the BioMEMS region. For me, this workshop is very, very helpful, and especially the session by the Raghav sir and the doctor who explained about the what are the different effects as a researchers will get when we are keep on working on the in front of the laptop, what type of kidney effects we are getting, and what are the things in BioMEMS, how we can identify these all diseases. And that talk very impressive talk, madam. And one more, once again, I would like to congratulate all the FDP organizers team for planning such a wonderful FDP for the 5 days. All the speakers are eminent speakers, and they are given the best inputs for us to extend our research. Thank you.
Thank you, Lakshman sir. Thank you for your feedback. I again call up SSS ARCI DST who is trying to speak. Sir, if you are not able to reach through voice, kindly type in the chat box and I can read that out for you. We'd welcome some more participants to give their feedback.
Okay, yeah, Preeti, so we can move to the next proceedings.
Yes, sir. So I thank all the participants for having been very attentive and also enthusiastic through all the 14 sessions, and for encouraging us through your continuous feedback in the chat box, and for attending all the sessions with sincerity. And I hope this has added a lot to your knowledge and given a cerebral grilling too. Now I invite Dr. Kaushik Guha sir to give away his vote of thanks.
Yeah, thank you. So it is a privilege for me to give a vote of thanks at the closing ceremony. Honorable Director sir, Honorable Chairman sir, Honorable the HODEC, Dr. K.L. Vaishnav sir, Honorable Dr. S. Raghavan sir, presenting among us. Throughout the entire 5 days, I have seen the sir has attended all the sessions. The other eminent speakers, the other delegates, the distinguished participants. So I, on behalf of my team members and the entire community, first of all, spread my most sincere thanks to the Almighty God for helping us to organize the program successfully. Then I would like to thank the AICT ATAL Academy for associating with our institution, NIT Silchar, and jointly making it possible for this opportunity and providing a platform for interaction with dignitaries to gain knowledge and resources. I wish to extend my deep appreciation to the ICT for sponsoring this FDP and made it possible for all of us to be a part of this program. Then on behalf of the organizing committee, I would like to extend my heartiest thanks to our Honorable Director, sir, Honorable Director of NIT Silchar, Professor Shivaji Bandyopadhyay, for his presence in the function. Thank you, sir, for enlightening us with your inspiring and motivating words. Sir, you have inspired us to do our best and stand as a pillar of power with deep sense and appreciation. We thank you for your untiring efforts in making the partnerships between Silchar and the other renowned organizations across the globe. Next, I would like to thank our Dean Research and Consultancy, and who is also the patron of this program, Professor H. Boisho, whose active support has always been there whenever needed, and I extend my sincere gratitude towards him. I would like to thank our chairperson of this FDP and president of Institute Innovation Cell NIT Silchar, Professor F. Talukdar, whose tireless effort and disciplined way of department has always been a support for success in an adverse situation. Wholeheartedly, I must thank to our beloved HOD EC, Dr. K. Vishnav sir, for his exemplary support and guidance for organizing such an event. Thank you, sir, for assisting and encouraging all of us always. Next, I would like to thank all the eminent speakers of the FDP who managed amiably, agreed to take some time out from their busy schedule and visit us over here and thereby enlighten us with their knowledge and expertise in the field of BioMEMS and medical devices. Their lecture sessions must have definitely encouraged young minds and talent to pursue the research and work in this field. It has been our tribute to host all the members and participants of the FDP. I am thankful to all the participants for joining here and attending all the sessions. We have been fortunate to have a distinguished participants from academics, industry, and other areas. I am very thankful to the entire participants. I am sure that our institution will continue to get significant provision from diverse groups in the near future. Next, I would like to thank our esteemed faculty, Dr. T.R. Lenka, IEEE EDS Student Branch Chapter Faculty Advisor of NIT Silchar, for his support to associate this FDP with the IEEE banner. So because this FDP is also organized in association with the IEEE EDS Student Branch Chapter NIT Silchar and also IEEE Nanotechnology Council Chapter NIT Silchar. So thank you, Dr. T.L. Lenka, for helping me. I take this occurrence to thank the entire administration of NIT Silchar as well as the Dean PND, specifically Associate Dean PND, FIC Networking, for helping us to conduct the program in virtual mode and smooth and hassle-free. I must remark a proficient sense of gratefulness to all of our colleagues for their kind support and cooperation. So next, the last but not the least, that I would like to thank all our student volunteers, especially Satish, Preeti, Naushad, Saurabh, Ganraj, Oshar, Anusha, and Swagata, and so many other members, the main workforce behind the workshop, behind this FDP, whose enthusiasm and dedication have been inspirational, whose sincere commitment and timeless effort have made this 5 days FDP a very, very successful event. Thank you all. So let us have a claps for all the student volunteers. Then just because this is a virtual platform, so all the participants are connected after some time, after maybe around 5 minutes, so we'll close the program. So before that, we want to announce from the Department of EC and also the NIT Silchar for the external participants that, okay, we are also hosting or organizing another program very soon in the month of September. It is a IEEE Electron Device Society Summer School on recent trends in nanotechnology and electronics devices, circuits, and system perspectives. So I hope that if you have enjoyed the participation in NIT Silchar with this FDP also, I request you, those who are also working in this field, IEEE electron device group, microelectronics, VLSI, semiconductor device, you can also welcome to join on our next program. Obviously, this program is very going to be also very interesting and beneficial. So all the eminent speakers are also there in this our upcoming program in IEEE Summer School. You can see. So the all the eminent speakers, also from abroad and also from our country, we have picked up all the eminent speakers to give the direction and the most recent research that has been going on the electron device area. So next, I also want to highlight that also our Department of Electronics and Communication Engineering in NIT Silchar, we also organizing the second international conference on micro nano electronic devices, circuits and systems. It will be held from 29 to 31 January in 2022 next year. So we can see also that the area or the call for papers this have spans diverse topics. So we are also expecting the papers in this field, micro nano electronic devices, micro nano electronic circuits, and micro nano system, because MEMS and BioMEMS are also there in this. So those, I think I would request you please consider this conference and consider your technical digest to our conference, so that I am sure that also you will enjoy a lot in this by participating in our upcoming conference also. So this is the closing time. We have reached at the end of the program. So we will close the program by playing a national anthem, because we from NIT Silchar wish you a very happy 75th anniversary of India's independence, specifically this year 2021. So this is what generally we can say, this is the Azadi Ka Amrit Mahotsav. So we want to play the national anthem and then we will close the ceremony, valedictory ceremony. So Saurabh, can you play?
Yes, sir. You stop sharing first, then
जनगण मन अधिनायक जय हे भारत भाग्य विधाता, पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा, विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा, तव शुभ नामे जागे, तव शुभ आशीष मांगे, गाहे तव जय गाथा, जन गण मंगलदायक जय हे भारत भाग्य विधाता, जय हे जय हे जय हे जय 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 हे.
Thank you all. So now